There's a photograph from Mars that NASA hasn't officially released, but you can find it online right now if you know where to look. It shows a faint blue anomaly at the precise sky coordinates where an interstellar object, designated 3 Atlas, passed during its closest approach on October 3rd, 2025. The image came from Perseverance's mast CAM-Z, camera stacked by a citizen scientist, endorsed by Harvard astrophysicist Avi Loeb, and immediately disputed by skeptics, who see processing artifacts where others see confirmation. Here's why it matters. Every space-based telescope tracking this object showed carbon dioxide chemistry and neutral to greenish color. Blue doesn't fit. Blue suggests either instrumental error, atmospheric effects, or something with reflective properties that aren't commentary. Add 7 other statistical anomalies near ecliptic trajectory, nickel without iron, sunward morphology, and you've got an object that strains natural explanations. The leaked image is the crack in the narrative, the moment when information escaped institutional control and forced a conversation that's still unresolved. Stay until the end, because what this image reveals isn't on the surface. It's in the silence that followed. Before we dive into what this all actually means, consider subscribing if you enjoy these late-night explorations, and tell me in the comments where you're watching from tonight. I'd also love to hear your thoughts. Do you think this image is real or part of a bigger cover-up? Let's get into it. Part 1. The leak that shook the community. Someone leaked an image from Mars, and it might just rewrite the rules of everything we thought we knew about what moves between the stars. On October 3rd, 2025, an interstellar object designated 3 Atlas made its closest approach to Mars. 29 million km separated the red planet from something that shouldn't have been there, something that traveled across the void between solar systems to arrive at our cosmic doorstep with timing so precise it bordered on suspicious. Space agencies around the world had their instruments trained on the flyby window. NASA, ESA, observatories across Earth and in orbit, all watching, all waiting for the data that would tell us what this thing really was. The public expected images, spectroscopy, confirmation. What they got instead was silence. And then something far more interesting. A stacked image appeared on blue sky, posted by astrophotographer Simeon Schmaus. It showed frames from the Perseverance rover's MASCAM-Z instrument, carefully layered to reveal faint signals, invisible in single exposures. At the predicted sky position of 3 Atlas, there it was, a smudge, faint, diffuse, barely there against the Martian night, but undeniably blue. Aviv, the Harvard astrophysicist who has made a career of asking uncomfortable questions about interstellar visitors, amplified the image with a simple credit line that gave it the weight of institutional provenance. NASA divided by JPL, Caltech divided by ASU, divided by Simeon Schmaus. He described it as a faint smudge at the predicted location captured by stacking multiple MASCAM-Z frames. If this was real, it would represent the first time a Mars surface instrument had detected an interstellar object in real time during a close approach. The image electrified a community already primed for controversy. For weeks, space-based instruments had been painting a picture of 3 Atlas as something unusual, but ultimately explicable. Carbon dioxide rich, sometimes appearing faintly greenish in processed composites, with an extended coma that stretched hundreds of thousands of kilometers into space. The spectroscopy was weird but interpretable. The morphology was strange but modelable. Everything pointed toward an exotic comet, formed in conditions we don't see in our own solar system, ejected from some distant planetary system, and now passing through ours on a trajectory that would never repeat. But this image from Mars showed blue, not green, not neutral, blue. That single chromatic discrepancy opened a fracture line through the online astronomy community that would only widen in the days to come. Lowe's framing carried weight because he had established a pattern. His posts about 3 Atlas had been building a case for weeks, stacking anomaly upon anomaly, each one individually explainable, but collectively unsettling. A sunward glow that defied typical cometry, behavior spectroscopic signatures that suggested industrial metal ratios, polarization measurements that fell outside known comet families. And now this, a blue smudge from the surface of Mars, leaked through informal channels, while official data remained locked behind agency review processes. The provenance mattered. This wasn't a NASA press release. It wasn't peer-reviewed data published in Nature or the Astrophysical Journal. It was a citizen scientist stack shared on social media, endorsed by a controversial but credentialed astrophysicist, and immediately weaponized by both believers and skeptics. What would it mean if the image was legitimate? The apparent surface brightness would have to be high enough for a non-astronomical instrument designed for daylight geology to capture it through multiple exposures that implied either favorable viewing geometry, an unusually reflective surface, or something emitting or scattering light far more efficiently than a typical dust coma. The conservative interpretation suggested we were seeing forward scattered sunlight from the same carbon dioxide-rich coma that JWST and SphereX had already characterized. The geometry was right. Mars sat along a favorable line of sight during the flyby. Multiple stacked frames could absolutely pull a faint extended source out of noise. But the speculative interpretation was far more provocative. What if the signal came not from diffuse gas and dust, but from a structured reflective surface? What if 3 Atlas wasn't a comet at all, but something designed to look like one from a distance, only revealing its true nature under the scrutiny of close-approach observations? The fracture line in the audience was immediate and visceral. Believers saw confirmation of what Lowe had been suggesting all along. This was the smoking gun. The first Mars surface confirmation of an interstellar visitor that might not be natural. The stacked frames revealed exactly what the models predicted: a faint but detectable signal at the correct sky coordinates, visible only through careful processing. Skeptics saw artifacts, timing coincidences, and the dangers of pattern recognition in noisy data. They raised legitimate concerns about processing methodology. How were the frames aligned? What color channel weighting was applied during the stack? Were there cosmic ray hits or hot pixels at that location that could masquerade as a real signal? Without access to the raw frames, independent verification was impossible, and that impossibility became its own narrative fuel. The color mismatch gnawed at everyone paying attention. Space-based instruments, with carefully calibrated spectroscopy, had shown carbon dioxide dominating the coma, with water vapor as a minor component, and trace metal emissions that included neutral nickel and iron atoms. Carbon dioxide-rich come blue. They scatter sunlight, with a neutral to slightly greenish cast, depending on dust grain properties and viewing geometry. Blue implies something else: scattering from very small particles, perhaps specular reflection from a smooth metallic surface, or simply an artifact of how Mascam's biofilter array was processed during the stacking operation. The blue smudge raised more questions than it answered. And that was precisely why it mattered. In the gap between what we expected to see and what appeared in that leaked stack, an entire universe of speculation rushed in to fill the void. We need to understand what happened here. Not just the image itself, but the mechanics of how it leaked. why Mastcam Z was a strange choice for this kind of observation, and what the color tells us about either the object or the instrument. Then, we need to ask the harder question. If this detection is real, what does it imply about the nature of 3 Atlas? And if it's not real, why did it resonate so powerfully with an audience already primed to believe that something extraordinary was hiding in plain sight? Part 2. Anatomy of a supposed leak. The image didn't come through official channels, and that matters more than you might think. Simeon Schmaus posted his stacked Mastcam Z frames to Blue Sky on October 4th, 2025, approximately 24 hours after 3i Atlas made its closest approach to Mars. The post included technical details about frame selection, alignment methodology, and the coordinate prediction he used to determine where in the Martian sky the object should appear. Lowe picked it up almost immediately, incorporating it into a medium essay that framed the detection within his broader narrative about 3 Atlas anomalies. The credit line gave the stack institutional legitimacy, even though it bypassed every standard verification gate that NASA's Perseverance mission normally imposes on public data releases. This was citizen science at its most potent and most problematic. Potent because it demonstrated that curious individuals with the right skills could extract signals from public data that agencies hadn't yet highlighted. Problematic because without independent verification from other analysts using the same raw frames, we had no way to distinguish real signal from processing artifact. Stacking is a standard technique in astrophotography, used to pull faint targets out of noise by combining multiple exposures. The principle is straightforward. Random noise averages away across frames, while real signal accumulates. If you align 10 images of the same field and sum them, noise decreases by the rule of 10, while signal increases linearly. But the devil lives in the alignment. Small registration errors between frames can create chromatic artifacts, especially if the object is moving relative to the background stars. Color channel misalignment during the stacking process can produce off-hue glows that have nothing to do with the physical spectrum of the target. Atmospheric dispersion, even Mars's thin atmosphere, can separate colors differently at low elevations. And if the object is faint enough that it's only barely above the detection threshold in individual frames, confirmation bias becomes a real concern. We see what we expect to see, especially when looking for something we desperately want to find. Mastcam Z was never designed for this kind of work. It's a zoomable multispectral stereo camera system mounted on Perseverance's mast, optimized for geological surveys, landscape panoramas, and close-up rock texture analysis. The instrument has 11 narrow-band filters, spanning visible to near-infrared wavelengths, allowing it to characterize mineral compositions and atmospheric properties during Martian daylight. It can zoom from 34 mm to 110 mm equivalent focal length, giving it flexibility for both wide-field context and detailed targets. But it's fundamentally a daytime geology camera, not a deep sky imager. It lacks the long exposure capability, tracking precision, and low noise performance of dedicated astronomical instruments. Its typical use case involves sunlit crater floors and wind-streaked dunes, not faint interstellar point sources transiting the night sky. The field of view and pixel scale create additional complications. Even at maximum zoom, Mastcam Z sees a relatively wide patch of sky compared to a telescope. Faint off-axis light sources can create internal reflections, ghost images that appear at predictable locations based on the optical design. Sensor noise, especially in extended night exposures, produces hot pixels and cosmic ray hits that must be carefully filtered out during processing. Mars's atmosphere, while thin, still scatters sunlight even at night, particularly near the horizon. Dust suspended in the Martian air glows faintly in scattered twilight and starlight, creating a variable background that changes with atmospheric opacity and viewing elevation. All of these factors conspire to make marginal detections ambiguous. A faint smudge could be real, or it could be the intersection of half a dozen instrumental and environmental effects that just happen to align at the predicted coordinate for 3I Atlas. The raw feed question became central to the debate within hours of the leaked stack appearing. If Schmaus had genuinely detected 3 Atlas in Mastcam Z frames, then in principle, any other analyst with access to the same raw data could reproduce the result. NASA makes Perseverance's raw images publicly available through the mission's online archive, typically within a few days of acquisition. But reproducibility requires knowing exactly which frames were used, what timestamps they carried, how the rover was pointed, and what calibration steps were applied before stacking. Without that metadata, independent verification becomes a fishing expedition. You can look at dozens of night sky frames from the relevant observing window and never find the exact combination that produced the original stack. And if you do find candidate frames but can't reproduce the smudge, does that mean the detection was spurious? Or just that you used a different processing methodology? Alternate pathways for confirmation existed and were publicly discussed in the days following closest approach. Mars orbiters, particularly the Mars Reconnaissance Orbiter's high-rise camera, Mars Express, and the ExoMar Trace Gas Orbiter, all had potentially superior geometry for detecting 3 Atlas during the flyby window. Lowe himself flagged high-rise as a critical asset in his pre-fly medium essays, noting that its high-resolution imaging could constrain the object's diameter by measuring whether any single pixel showed anomalous brightness. High-rise's spatial resolution of about 30 kilometers per pixel at 3I, Atlas's distance meant that a sufficiently bright compact source could saturate individual pixels or create a detectable point spread function, even if the object was much smaller than the pixel scale. But high-rise data, like Mastcam Z data, goes through internal review before public release. The gap between acquisition and publication can stretch from days to weeks, depending on mission priorities and analysis complexity. Benign explanations for the smudge were plentiful and worth considering seriously. Hot pixels are common in CMOS sensors, particularly during long exposures or in thermally variable environments. A single malfunctioning photo site at the predicted coordinate location would produce exactly the kind of faint stationary signal visible in stacked frames. Cosmic rays strike detectors constantly, creating bright transient events that, if they happen to hit the same pixel location across multiple frames by chance, could masquerade as a real astronomical source. Dust modes on the instrument's protective window or internal optical elements can scatter light in complex ways, producing faint halos or off-axis glows. Compression artifacts in the JPEG or PNG files used for public distribution can create banding, color shifts, or spurious features that weren't present in the raw, uncompressed frames. Misregistration during the stacking process, particularly if frames were taken at slightly different pointings or focal lengths, can create edge effects and chromatic fringes. And finally, there's always the possibility of a real but unrelated background star that happened to lie near the predicted path of 3 Atlas, creating a genuine astronomical signal that has nothing to do with the interstellar object. The blue color remained the most provocative element, and also the most suspicious. White balance assumptions matter enormously in RGB imaging. Mastcam's raw frames capture light in 11 separate spectral bands which must be combined and color balanced to produce the kind of visually intuitive RGB image that humans interpret easily. Different assumptions about illumination conditions, atmospheric transmission, and target properties can shift the color balance dramatically. A processing pipeline optimized for Martian daylight, where the illumination spectrum is reddened by atmospheric scattering, might wake color channels in ways that produce artifacts when applied to faint night sky targets. Subtle differences in how the BOF filter array is demosaic during raw conversion can introduce color shifts, especially at low signal-to-noise ratios, and atmospheric path effects, even on Mars, can preferentially scatter shorter wavelengths, depending on dust loading and viewing geometry. The truly colorless or neutral source might appear blue if the processing assumed a redder background than actually existed. But there's a more intriguing possibility, one that requires careful framing because it ventures into speculation. If 3 Atlas has a reflective metallic surface rather than a diffuse dust coma, certain white balance assumptions applied during image processing could bias the color toward blue under Martian night sky conditions. Metals like aluminum or stainless steel have relatively flat reflectance spectra across visible wavelengths, meaning they reflect sunlight without significant color preference. But if the processing pipeline expected a warm illumination source, as it would for daytime Mars imaging, and then encountered a relatively neutral reflector, illuminated by unfiltered sunlight, reflected off the Martian surface or atmosphere, the color correction could overcorrect and push the apparent color blue. This is speculative and less likely than simple processing artifacts, but it illustrates how much we need raw frames and transparent methodology to distinguish physical reality from instrumental effect. The color mismatch is a flag demanding reproducibility. We cannot conclude physics from a colorized stack processed through unknown pipelines and shared via social media. We need the raw frames. We need independent analysts applying diverse processing techniques and comparing results. We need spectroscopy from Mars-based instruments, if any, exist with the right capabilities, or at minimum, multi-band photometry that would tell us whether the blue tint is real or artificial. Until we have those confirmations, the smudge remains exactly what its name suggests: a blur, a question mark, a provocation. And yet, the question lingers. What if it's real? What if, color aside, Mascam Z genuinely captured 3I Atlas transiting the Martian night, bright enough and close enough for a surface imager to detect it through stacking? What would that tell us about the object's apparent brightness, its surface properties, its geometry relative to Mars during closest approach? Those questions lead us toward implications that are harder to dismiss with hand-waving about hot pixels and compression artifacts. Because if the detection is real, then 3E Atlas is brighter, closer, or more reflective than we had any right to expect. And brightness in astronomy is almost always a proxy for size or surface area, which brings us to the uncomfortable realization that this object might be much, much larger than the interstellar visitors we've seen before. Part 3. A timeline of silence and coincidence. The week of October 1st through 7th, 2025 was supposed to deliver answers. Instead, it delivered questions wrapped in silence and amplified by coincidence. Closest approach occurred on October 3rd at approximately 1,300 hours UTC, with 3 Atlas passing 29 million km from Mars. The observation window extended several days on either side, with prime viewing conditions from October 1st through 7th. Lowe's pre-fly medium essays had set expectations. He anticipated data from multiple Mars orbiters, including the Mars Reconnaissance Orbiter's high-rise camera, ES's Mars Express, and the Exxon Mars Trace Gas Orbiter. He noted that Perseverance's Mascam Z could contribute night sky observations if the mission team chose to dedicate time to the target. He framed these observations as critical constraints on three atlases: size, composition, and morphology, potentially resolving ambiguities that Earth-based instruments couldn't address due to distance and viewing geometry. The community waited. The data feed stayed quiet. And in that silence, a narrative began to crystallize. Lowe has established a cadence over the years, and audiences have learned to recognize the pattern. He publishes essays stacking anomalies and raising questions ahead of official data releases from space agencies. He frames observations in ways that emphasize low probability coincidences and deviations from baseline expectations. He suggests artificial hypotheses alongside natural ones, treating them as equivalently worthy of investigation rather than extraordinary claims requiring extraordinary proof. This approach has made him simultaneously influential and controversial. His admirers see a scientist willing to challenge orthodoxy and ask uncomfortable questions. His critics see motivated reasoning and a tendency to find significance in noise. But regardless of where you stand on Lowe's methodology, his public writing creates anticipation. When he says observations are imminent and will resolve key questions, people expect resolution. When resolution doesn't arrive on the predicted timeline, speculation rushes in to fill the gap. The US government shutdown timing added fuel to a fire that was already smoldering. A partial federal shutdown began on September 30th, 2025, affecting discretionary programs, including some NASA operations. Public affairs offices scaled back. Non-critical mission activities were postponed. Data release schedules slipped. None of this was unusual or unprecedented. Shutdowns affect public communication more than core mission operations. The Mars orbiters and Perseverance continued functioning. Science data continued being collected and downlin. But the external interface, the press releases and curated image galleries that translate raw telemetry into public-facing narratives went quiet. Creators and commentators latched onto the shutdown as a narrative hook. Why did the shutdown happen to coincide with the 3E Atlas flyby? Was it merely bad timing? Or was there a deeper reason agencies might want to throttle public communication during this particular observation window? To be absolutely clear, there is no evidence that the shutdown was engineered to suppress 3 Atlas data. Shutdowns result from congressional budget impasses, not mission-specific considerations. And even during shutdowns, NASA's deep space missions continue operating because they're considered essential infrastructure. The Mars Reconnaissance Orbiter doesn't shut down. Perseverance doesn't stop taking images. Data doesn't stop flowing to ground stations and archives. What does slow down is the human-intensive process of curating, contextualizing, and releasing that data to the public. The shutdown timing was coincidental, but coincidences in the context of already heightened speculation become load-bearing pillars of conspiracy narratives. Whether they deserve that weight or not, the diffusion loop worked exactly as social media platforms are designed to work. Schmaus's Blue Sky post spread to X, formerly Twitter, where it was quote tweeted and screenshot dozens of times. It appeared on Reddit's astronomy and UFO-related subreddits, where comment threads exploded into hundreds of replies arguing provenance and interpretation. Blogs like The Debrief picked up the story, amplifying the Perseverance faint smudge meme with headlines that walked the line between factual reporting and provocative framing. Each amplification stage added new audiences, new interpretations, new layers of speculation divorced from the technical details of the original stack. Within 72 hours of the image appearing, it had achieved a kind of public reality independent of whether it represented genuine detection or processing artifact. The smudge existed not just in the frames, but in the collective consciousness of everyone following the story. And that collective consciousness began demanding answers that official channels weren't providing on the expected timeline. This pattern has precedents. ʻOumuamua's ambiguity window lasted months, with initial observations suggesting a highly elongated tumbling object and subsequent non-gravitational acceleration measurements implying either asymmetric outgassing or, in Lowe's controversial framing, a light sail. The lack of detectable comb or dust led to extended debates about whether it was a comet, an asteroid, or something else entirely. The data dribbled out slowly through preprints and peer-reviewed papers, while online communities speculated wildly. M1, the interstellar meteor that Lowe's team claimed to have retrieved debris from in the Pacific Ocean, followed a similar trajectory. Initial detection and orbit reconstruction were followed by expedition planning, oceanic retrieval, and laboratory analysis of metallic spherules that Lowe argued showed anomalous isotopic ratios. Each stage took months, with official confirmations lagging behind Lowe's public essays. Critics disputed interpretations. Replication attempts failed or supported alternative explanations. But the narrative momentum once established proved difficult to reverse, even when technical objections mounted. Information lag is common in complex observational campaigns, and it doesn't imply cover-up. Spacecraft data must be downlinked, decompressed, and calibrated. Pointing information must be correlated with precise ephemerides for the target. Raw frames must be bias-subtracted, flat-fielded, and assembled into coherent image sequences. Spectroscopic data requires wavelength calibration and extraction of one-dimensional spectra from two-dimensional detector arrays. All of this takes time, particularly when the observation wasn't part of the primary mission plan and requires special processing. Mars orbiters have primary objectives related to Martian geology, atmosphere, and climate. Observing a transient interstellar object is a bonus science opportunity, but it's not the reason those spacecraft exist. Priority processing goes to Mars data. 3 Atlas observations get handled when analysts have bandwidth, which during a government shutdown and overlapping mission milestones might mean days or weeks rather than hours. But silence, even when explicable, creates fertile ground for speculation. The analytical takeaway is straightforward, but uncomfortable. Absence of evidence is not evidence of absence, but in a high-stakes, high-attention observing campaign, absence of communication functions as evidence of something. Maybe it's just bureaucratic inertia. Maybe it's caution in the face of extraordinary claims, a reluctance to release preliminary data that might be misinterpreted. Maybe it's the collision of overlapping communication barriers, the shutdown, plus mission priorities, plus internal review timelines, all conspiring to create a gap where audiences expected immediate gratification. Or maybe, and this is the edge of speculation, that we must acknowledge even as we resist it. Maybe the initial data showed something sufficiently ambiguous or provocative that agencies chose to triple-check before making any public statement, not because they're hiding aliens, but because the consequences of being wrong in either direction are enormous. We need to interrogate the color contradiction. Now, why does the smudge appear blue when every other instrument characterizing 3 Atlas shows carbon dioxide-rich neutral to greenish scattered light? That single chromatic discrepancy carries more weight than almost anything else in this story, because it's quantifiable, reproducible, if we get access to raw frames, and diagnostic of either instrumental artifact or unexpected physics. And, after we understand the color, we need to confront the harder question. If the leak is real, what does it tell us about the nature of 3E Atlas? Part 4, the green that turned blue. The mainstream instrument picture painted 3E Atlas in shades of green and neutral gray with a composition dominated by carbon dioxide and a morphology that stretched preferentially toward the Sunday. The leaked Mars image showed blue. That chromatic contradiction demands an explanation, and the explanation matters because color is physics. JWST's near-infrared spectrograph observed 3 Atlas in late September 2025, capturing high-resolution spectra of the coma that revealed carbon dioxide as the dominant volatile species. The CO2-to-water ratio measured approximately 8:1, far higher than typical solar system comets where water dominates. This finding was robust, published in a preprint on AR Grief, and confirmed by NASA's Goddard Space Flight Center in their online research highlights. The carbon dioxide coma was sunward enhanced, with outgassing rates significantly higher on the sun-facing hemisphere than the anti-Ola side. Water was present but subdued, concentrated in a relatively compact region near the nucleus. This composition suggested formation conditions near a carbon dioxide ice line, possibly in the outer regions of a planetary system where carbon dioxide remains frozen while water has already been lost to earlier heating events. Or it suggested radiation processing of surface ices, where cosmic rays and stellar UV photons had preferentially removed hydrogen-rich volatiles over geological timescales. Either way, the spectroscopy was unambiguous. This was a carbon dioxide-rich object, not a water-rich one. Sphere X, NASA's space-based infrared observatory, mapped 3 Atlas's extended coma in early October, revealing carbon dioxide signatures extending outward from the nucleus to distances exceeding 348,000 kilometers. This extended coma confirmed that outgassing was vigorous and sustained, not a transient event or localized jet. The morphology showed broad emission, consistent with surface or near-surface sublimation driven by solar heating, exactly what you'd expect from a natural comet responding to increased insulation as it approached perihelion. The Sphere-X data complemented JWST's spectroscopy, providing spatial context for the composition measurements. Together, these observations established that 3 Atlas was wrapped in a massive, extended envelope of carbon dioxide, gas, and dust, visible across a huge swath of the inner solar system. Hubble Space Telescope imaging revealed morphology that was unusual, but not unprecedented. The most striking feature was a diffuse sunward glow, an anti-tail extending preferentially toward the sun rather than away from it. Classic comets show anti-Ola tails, dust and ion structures pushed outward by solar radiation pressure and the solar wind. Anti-tails extensions that appear to point sunward result from viewing geometry and the distribution of dust grains along the comet's orbital path. When we see a comet nearly edge-on, dust grains released earlier in the orbit can appear projected toward the sun, even though they're physically trailing behind. 3. I Atlas showed this geometry, but with an aspect ratio that was extreme. Lowe and his collaborator, Eugene Quito, noted that the sunward extension was approximately 10 times longer than its width, creating a needle-like structure in processed images. Modeling suggested that this reflected anotropic emission from a hot dayside hemisphere, with dust and gas preferentially released from regions directly illuminated by the Sunday. The geometry was odd, but it was modelable within the physics of natural cometary activity. So what color should we expect from a carbon dioxide-rich coma? This is where things get subtly complicated. Pure gas has no color in the visible sense. We see gases through emission or absorption lines, not through scattered continuum light. What we see when we look at a comet is sunlight scattered by dust grains suspended in the coma. The color of that scattered light depends on grain size, composition, and the wavelength dependence of scattering efficiency. Carbon dioxide itself doesn't impart a green color. But many comets appear greenish in images because of emission from diatomic carbon C2, which produces strong green emission bands around 510 nanometers when excited by solar UV radiation. 3. I. Atlas hasn't shown strong C2 emission, at least not in published spectra to date. The expected color from dust scattering in a carbon dioxide-rich coma, absent strong emission lines, would be neutral to slightly reddish, matching the intrinsic color of sunlight with modifications from dust grain properties. Some composite visualizations might show a faint greenish tint if processing algorithms enhance weak emission features. But bright saturated blue is not on the menu. The blue smudge from the leaked mile stack is therefore eyebrow-raising from a physics standpoint. Blue light scatters more efficiently than red light off very small particles. This is why Earth's sky is blue, and why distant mountains appear blue tinged through atmospheric haze. Scattering dominates when particle sizes are much smaller than the wavelength of light. If 3 Atlas's coma contained an unusual population of very fine dust grains or aerosol particles, and if the viewing geometry from Mars emphasized forward scattering through this material, you could in principle get a blue scattered light component. But JWST and SphereX didn't report anything suggesting a dominant population of submicron particles. The dust grain size distribution inferred from those observations was consistent with typical cometary dust spanning from submicron to millimescales, with most mass in larger grains. There's no obvious physical reason for a carbon dioxide-rich coma to appear blue in scattered sunlight, so we return to instrumental and processing explanations. A non-astronomical camera, like Mastcam-Z, designed for daylight geology under Martian illumination conditions, uses color calibration routines optimized for those conditions. The Martian surface is predominantly red due to iron oxide dust. The atmosphere scatters light with a distinctly salmon hue during the day. Mastcam's white balance algorithms are tuned to render rocks and landscapes in colors that geologists can interpret. When you point that same instrument at a faint astronomical target at night, you're operating far outside the intended use case. The color calibration may simply not be appropriate. If the processing pipeline assumes a warm reddish illumination spectrum and then encounters a relatively neutral source, the color correction could overcorrect, pushing the apparent color toward blue. This is a boring explanation. It's also the most likely one. Another hypothesis, clearly speculative, considers aggressive noise suppression or channel miswiring during the stacking process. If the red channel had higher noise than the blue and green channels in the individual frames, an analyst might choose to downweight red to avoid introducing spurious features. Or if the frames were taken through different filter combinations and then composited into an RGB image, the filter choices might not map cleanly onto true color. Mastcam's filters include narrow bands that don't correspond exactly to standard RGB wavelengths. Combining filters to create a visually intuitive color image requires assumptions about how to weight each channel. Different assumptions produce different colors, especially for faint, low signal-to-noise targets. This channel misweighting hypothesis is testable if we get access to the raw data, but absent that access, it remains speculation. The least likely hypothesis, but one worth stating explicitly because it's circulating in discussions, invokes a reflective metallic surface. If 3 Atlas is not a diffuse coma, but a compact structured object with a reflective exterior, certain white balance assumptions could bias the color toward blue under Martian night sky conditions. Metals have relatively flat reflectance across visible wavelengths. They don't inherently appear blue unless they're coated or textured in specific ways that preferentially reflect shorter wavelengths. Stainless steel looks gray. Aluminum looks gray. Polished titanium looks gray. But if the image processing expected a reddish illumination source, and encountered neutral reflectance, the color correction might swing the processed result blue. This is mechanically possible, but requires two things to be true simultaneously. First, 3i Atlas must be a reflective structure rather than a diffuse coma. Second, the processing pipeline must have misapplied color calibration in exactly the right way to produce a blue artifact from a neutral source. The conjunction of these requirements makes this hypothesis weak, but not impossible. The bottom line is stark and uncomfortable. We cannot conclude physics from a colorized stack processed through unknown methodologies and shared outside formal verification channels. The color mismatch between the blue Mars smudge and the neutral to greenish presentation from space-based instruments is a red flag, unintended, demanding reproducibility from raw frames. We need multiple independent analysts processing the same data with transparent, documented methods. We need multi-band photometry from ʻOumuamua. If those bands were captured, allowing us to reconstruct the spectral energy distribution and determine whether the blue tint is real or artifact, we need cross-checks from other Mars-based assets, if any, obtained data during the flyby window. And we need honest acknowledgement that without these confirmations, the smudge tells us more about image processing than it does about the object. But color aside, assume for a moment that the detection itself is real. Assume that Mascom genuinely captured 3 Atlas transiting the Martian night at the predicted coordinates. Faint, but present. Visible only through careful stacking, but undeniably there. What would that imply? That question leads us toward uncomfortable territory, because brightness in astronomy is almost always a function of either size or reflectivity. And if 3 Atlas is bright enough for a Mars surface imager to detect it at 29 million kilometers, then it's either bigger, closer, or more reflective than we had any right to expect from an interstellar comet. Which brings us to the implications we can't ignore. Part 5. What the leak implies, if it's real. Apparent surface brightness is not a casual observation. It's a physical constraint that connects luminosity, distance, and viewing geometry into a tight web of implications. If ʻOumuamua detected 3 Atlas through stacked frames, then the object was bright enough, extended enough, or favorably positioned enough for a non-astronomical camera to pull it out of the Martian night sky. That sentence contains multiple possible truths, and we need to disentangle them carefully. The conservative interpretation assumes the stacked signal represents coma, the extended envelope of gas and dust that JWST and SphereX already confirmed. ʻOumuamua coma can be remarkably diffuse, spreading light across huge solid angles and appearing faint per unit area, even though the integrated luminosity is high. But they can also exhibit surface brightness enhancements in specific directions, particularly forward scatter geometries, where sunlight bouncing off dust grains is directed preferentially toward the observer. The Mars flyby geometry placed Perseverance along a favorable sightline for observing 3E Atlas's sunward hemisphere, the region where JUPI detected enhanced carbon dioxide outgassing, and Hubble observed the elongated anti-tail feature. If Mars sat along a forward scattering direction, the apparent surface brightness of the coma could have been significantly elevated compared to what Earth-based observers saw. This is entirely consistent with natural cometry physics. It requires no exotic composition, no structured surface, no engineered properties, just geometry and dust optics doing what they do. But there's tension in this interpretation. ʻOumuamua is not a sensitive instrument for faint extended sources. Its detector noise, red noise, and dark current are optimized for short exposures under bright illumination, not long integrations of faint, diffuse targets. Even with stacking, pulling an extended coma out of noise requires that the coma's surface brightness exceeds some minimum threshold per pixel. If 3I Atlas's coma was as diffuse as the Sphere X mapping suggested, spreading carbon dioxide emission across hundreds of thousands of kilometers, then the surface brightness at Mars's distance should have been extremely low, probably below Mascam's practical detection limit. Even with aggressive stacking, the fact that a signal appeared, if it's real, suggests either that the coma was more concentrated than the large-scale mapping indicated, or that we're seeing something with higher intrinsic surface brightness than a typical diffuse coma. The speculative interpretation invokes a reflective or structured surface, rather M-continu, than a diffuse gas envelope. If 3I Atlas possesses a compact, highly reflective exterior, perhaps a metallic shell or coating, then its apparent brightness would scale very differently than a comet's coma. A reflective sphere, or ellipsoid, scatters sunlight efficiently from its illuminated hemisphere, concentrating brightness into a small, angular area, rather than spreading it across a vast, diffuse envelope. The surface brightness of such an object, even at 29 million km, could exceed that of a diffuse coma by orders of magnitude. This would make it detectable by an instrument like Mascamid, despite the unfavorable observing conditions. The geometry would matter enormously. If Mars observed 3 Atlas near a favorable phase angle, where specular reflection directed sunlight toward the rover's position, the brightness could spike dramatically. This interpretation requires abandoning the assumption that 3 Atlas is fundamentally a comet, and embracing the possibility that it's something else entirely, something with engineering rather than geology written into its surface properties. Loewers framed the size question aggressively in his medium essays, arguing for a nucleus diameter of 5 kilometers or larger based on brightness constraints and non-gravitational acceleration measurements. His reasoning connects multiple observations into a chain of inference. The object's absolute magnitude, the brightness it would have at a standard distance from both sun and observer, constrains the product of size and reflectivity. If you assume a typical cometary albedo around 4%, meaning the surface reflects 4% of instant sunlight, the brightness measurements imply a diameter of several km. The non-gravitational acceleration, the way 3-2 Atlas's orbit deviates from pure Caprian motion due to outgassing thrust, provides an independent constraint. For a given outgassing rate inferred from coma brightness, lower mass implies higher acceleration. The observed acceleration is relatively weak compared to 3I Atlas's brightness, which in Loew's analysis suggests high mass. High mass, combined with typical cometary density, implies large volume, hence the 5 kilometers estimate. He translates this into 33 billion tons, a number meant to convey the sheer scale of what we might be looking at. If 3 Atlas is genuinely 5 kilometers across, that places it in a different category than the previous interstellar visitors. 1I, divided by Mua, had estimated dimensions around 100 to 200 meters in its longest axis, a relatively small object by cometry or asteroidal standards. 2I divided by Borisov measured roughly half a kilometer in diameter, comparable to small solar system comets, but unremarkable in size. A 5 kilometers interstellar object would be dramatically larger, implying either that we've been extraordinarily lucky to intercept such a massive traveler, or that large interstellar objects are more common than small number statistics from 2 previous detections would suggest. This creates a detection rate paradox. If 5 kilometers interstellar objects pass through the inner solar system regularly enough that we've caught one in just a few years of looking, then where are all the smaller ones? Detection bias favors finding large, bright objects over small, faint ones. So the population of 100 Mikhail interstellar visitors should vastly outnumber the kilometer-scale population. We should have seen dozens of ʻOumuamua-scale objects before catching a single 3 Atlas-scale behemoth. The fact that we haven't suggests either that the size estimate is wrong, that interstellar object population statistics are wildly different than we assumed, or that 3I Atlas is not a random member of a statistical population, but something selected for specific properties. Mars versus orbiter leverage becomes critical for resolving these ambiguities. Lowe argued in his pre-flyby essays that the Mars Reconnaissance Orbiter's high-rise camera offered unique constraints because of its spatial resolution at 3 Atlas's distance. High-rise images Mars's surface at roughly 30 centimeters per pixel from low orbit, but when pointed at a target 29 million kilometers away, the effective pixel scale balloons to approximately 30 kilometers per pixel. That sounds useless for resolving details, but it's actually diagnostic for point source brightness. If 3 Atlas were a compact, reflective object, rather than a diffuse coma, and if it were bright enough, it could saturate individual high-rise pixels or produce a measurable point spread function, spreading light across a few pixels. By measuring which pixels lit up and how bright they got, analysts could constrain whether the signal came from an extended diffuse source or a compact high-surface brightness object. This is subtle work, requiring careful calibration and modeling. But in principle, the data exists, or should exist, if HiRISE actually observed the target during the flyby window. The Mars surface detection, if real, raises the stakes for these orbiter observations. If Perseverance's relatively crude camera caught 3 Atlas through stacking, then HiRISE, with its superior optics and imaging capabilities, absolutely should have detected it, if pointed correctly. The silence from HiRISE and other Mars orbiters in the immediate aftermath of closest approach therefore carries information. Either they didn't observe the target, which would be surprising given the advanced planning and public anticipation, or they did observe it, and the data are still being processed and verified before release, or they observed it and found something ambiguous enough, provocative enough, or complicated enough that agencies chose to delay public statements until they understood what they were looking at. None of these possibilities prove anything about the nature of 3I Atlas, but they all point toward the same conclusion. The Mars flyby was not a routine cometary observation. Something about this event elevated it beyond standard operating procedures. We're standing at the threshold between acts. The leak, if real, transforms from a curious anomaly into a load-bearing piece of evidence that 3 Atlas is not what we thought it was. But before we cross that threshold, we need to zoom out and examine the object itself, independent of any single controversial image. What do the mainstream scientific observations tell us? What patterns emerge when we look at 3 Atlas, not as an isolated mystery, but as the third interstellar visitor we've been able to study? The orbital plane oddities, the chemistry that doesn't match solar system templates, the polarization measurements that fall outside known families, the morphology that stretches toward the sun in ways that demand explanation. These are not leaks or rumors or processing artifacts. These are published, peer-reviewed, or at minimum pre-printed observations from flagship instruments, operated by agencies with no incentive to manufacture controversy. And when you stack them together, they paint a picture that is profoundly uncomfortable. Regardless of whether you believe in artificial hypothesis, they paint a picture of an object that shouldn't exist according to our baseline expectations of what interstellar space sends our way. That object and its implications are what we turn to now. Part 6. The 5 degrees mystery. Precision or accident. Imagine throwing a dart at a globe from across a room while blindfolded. Now imagine that dart against all odds, landing within 5 degrees of the equator. That's not quite the right analogy, because at least you aimed in the general direction of the glow. 3 Atlas arrived from interstellar space with no reason to prefer our planetary disk, no prior knowledge of where our planets orbit, no connection to the flat plane that defines the solar system's architecture. And yet, its trajectory lies within 5 degrees of the ecliptic, the plane containing Earth's orbit and most of the other planets. Avibe calculated the probability of such an alignment occurring by chance and arrived at a number around 0.2%, or about 1 in 500. That number is his framing derived from assumptions about how interstellar objects should be distributed if their arrival directions are truly random. Present that calculation with appropriate skepticism, because selection effects and small number statistics can inflate perceived improbability dramatically. But even with conservative assumptions, the alignment is striking enough to demand explanation. The orbital parameters are public and independently verified across multiple tracking systems. 3I Atlas follows a retrograde orbit, meaning it moves opposite to the planet's direction around the Sunday. The inclination, the angle between its orbital plane and the ecliptic, measures approximately 4.9 to 5 degrees, depending on which epic orbital solution you examine. For comparison, most solar system comets from the Oort cloud arrive on orbits with random inclinations, spanning 0 to 180 degrees with roughly uniform distribution. Long-period comets show no preference for the ecliptic, because the Oort cloud is a spherical distribution of icy bodies surrounding the Sun at vast distances. Interstellar space, by any reasonable model, should be even more isotropic. Objects ejected from other planetary systems have no memory of our system's orientation. Their arrival direction should sample the entire sky uniformly. A near-ecliptic trajectory is therefore, statistically speaking, unlikely. But unlikely is not impossible, and 5 degrees is not 0 degrees. Let's be precise about what the geometry means. An interstellar arrival exactly in the ecliptic plane would be extraordinary to the point of demanding non-natural explanations. 5 degrees off the ecliptic is unusual, but not absurd. It places 3I Atlas's trajectory within a broad band around the solar system's planetary disk, rather than randomly oriented through 3-dimensional space. The distinction matters because our intuition about coincidence, probability, is notoriously bad. Humans are pattern recognition machines, and we see design in randomness more often than we see randomness in design. A 5-degree inclination might represent the tail of a statistical distribution, the one arrival in hundreds that happens to come in nearly aligned, just because probability allows rare events to occur. Or it might represent something else. Earth's ecliptic contains not just Earth, but Venus, Mars, Jupiter, Saturn, and the other major worlds, all within a few degrees of the same plane. A trajectory aligned with that plane gives you natural encounters with multiple targets via pure ballistics. No course corrections required. 3. i.e. Atlas passed Venus at approximately 0.03 astronomical units on September 5, 2025. A close approach that delivered significant heating and likely triggered enhanced outgassing. It passed Earth at 1.23 AU on September 27th. It reached Mars on October 3rd at 0.2 AU. The encounter that generated the leaked Mascom-Z image and the extended observing campaign, and it's scheduled to pass Jupiter on March 16th, 2026 at approximately 1.9 AU. That's 4 planetary encounters in 6 months, a trajectory threading the needle through the inner solar system with almost suspicious efficiency. The counter view grounds us back in mundane statistics. With only 2 prior interstellar objects detected, 1 I divided by Mora and 2 I divided by Borisov. We don't have enough samples to establish what normal looks like. Bum came in at roughly 28 degrees inclination to the ecliptic, distinctly out of plane, but not perpendicular. Boris came in at approximately 44 degrees, more steeply inclined, but still not randomly oriented relative to the solar system's architecture. 2 objects are not enough to define a distribution. 3 is barely better. We might be seeing the beginning of a pattern where interstellar objects preferentially arrive within 30 or 40 degrees of the ecliptic, for reasons we don't yet understand, perhaps related to galactic dynamics, or the local interstellar medium structure, or we might be seeing pure chance, 3 dice rolls that happen to cluster in a visually striking way without representing any underlying cause. Distinguishing these possibilities requires detecting dozens or hundreds of interstellar visitors and mapping their arrival direction statistically. We're nowhere close to that sample size, but the delivered trajectory hypothesis gains traction when you layer the 5 degrees alignment onto the other anomalies that we're about to explore. Taken in isolation, a near-ecliptic orbit is curious but not dispositive. Combine it with timing that delivers close passes to Venus, Earth, Mars, and Jupiter in rapid succession. Add a sunward morphology that concentrates light and dust towards solar direction, rather than spreading it isotropically. Folding chemistry that doesn't match solar system comet templates. Stir in polarization measurements that fall outside known comet families, and cap it with the possibility, unconfirmed but tantalizingly suggested by a leaked Mars image, that the object has higher surface brightness than diffuse coma models predict. Each individual anomaly can be explained away, but the stack, the conjunction of multiple low-probability features in a single object, is what strains ordinary explanations. That stack is what Lowe has been building toward in his public essays, and it's what we need to confront honestly, even if we ultimately reject the artificial hypothesis. The ecliptic alignment carries one more implication worth stating explicitly. If 3 Atlas's trajectory was selected rather than random, then its approach vector was also selected. The object arrived from a specific region of the sky, a specific right ascension and declination that connects back to a specific direction in galactic coordinates. If this were an interstellar probe sent intentionally toward our solar system, the launch origin would lie along that arrival vector, somewhere in the deep past and deep distance, where the object's path extrapolates backward into interstellar space. Analysts have calculated that backward trajectory, the origin point, correcting for galactic rotation and the sun's motion through the local interstellar medium, lies in the general direction of the constellation Triangulum, but with enormous positional uncertainty, because we don't know precisely when the object began its journey. If it traveled for 10,000 years at its current velocity of roughly 29 kilometers per second relative to the Sun, it originated about 2.9 light-years away, well, within the nearest stellar neighborhood. If it traveled for 1,000,000 years, the origin point shifts dramatically due to the differential rotation of the galactic disk. Without knowing the launch date, we can't pinpoint the source, but we can say that the trajectory doesn't point toward any particularly interesting stellar system that we've identified as having planets or unusual properties. The origin is unremarkable, at least given our current data, which means either the source is something we haven't recognized as interesting, or the trajectory was not a straight shot from launch to arrival. Geometry is only one piece of the improbability stack. In isolation, it's provocative, but not conclusive. Combined with 6 other anomalies that Loeb has catalogued, it becomes part of a pattern that demands we take seriously the possibility that 3 Atlas is not a typical interstellar comet, if such a thing even exists. The statistical improbability stack is what we examine next, and it's where the case for something extraordinary becomes harder to dismiss with hand-waving about chance and selection effects, because when you have 7 independent anomalies, each individually unlikely but collectively present in a single object, you're no longer talking about a lucky dice roll. You're talking about either a fundamental misunderstanding of how interstellar objects behave, or an object that was designed to behave differently than nature's defaults. Part 7. The Statistical Improbability Stack. Harvey's Mars Approach Recap Essay lists 7 specific anomalies that distinguish 3 Atlas from baseline expectations of what an interstellar comet should look like. This is his framing, derived from his perspective as someone looking for evidence that might support artificial origins. Mainstream astronomers examining the same data would emphasize different features or frame the oddities as expanding our understanding of comet diversity, rather than challenging the natural hypothesis. But Loewy's list provides a useful structure for walking through what makes 3 Atlas genuinely strange, regardless of whether you ultimately interpret stranges as artificial or just exotic. The near-ecliptic alignment we've already covered. Low odds in Loewy's calculation, potentially explainable through selection effects or small number statistics, but striking enough to warrant attention. The timing adds weight to the geometric oddity. 3 Atlas didn't just arrive near the ecliptic plane. It arrived on a trajectory that delivered close encounters with Venus, Earth, Mars, and Jupiter within a 6-month window, spanning September 2025 through March 2026. This clustering of planetary flybys is not physically impossible under natural scenarios. Any trajectory roughly aligned with the ecliptic will necessarily pass near multiple planets because they orbit in the same plane. But the specific geometry and timing that places 4 encounters in rapid succession requires a particular arrival velocity and direction. Most ecliptic-aligned trajectories would pass above or below the planetary orbits, crossing the plane at points where no planets happen to be present. The fact that 3 Atlases crossing coincided with multiple planetary positions implies either fortuitous timing or selection. Loewy argues for the latter. Skeptics argue for the former, noting that we're more likely to detect interstellar objects that pass near Earth because our detection systems are biased toward finding things that come close. Both arguments have merit, and distinguishing them requires population statistics we don't yet possess. The sunward glow is where things start getting harder to explain with simple geometry. Hubble Space Telescope observations revealed 3 Atlases' morphology in stunning detail during mid-September 2025, capturing images that showed a diffuse elongation, preferentially directed toward the Sun rather than away from it. Typical comets display antiolar tails, structures pushed outward by solar radiation pressure and the interaction between the solar wind and the ionized coma. Some comets also display anti-tails, forward-pointing structures that result from viewing geometry. When we see the comet's dust trail edge on 3 Atlases' sunward feature was modeled in the Hubble analysis paper as day-side emission plus a weak antiolar tail, consistent with anotropic outgassing from the sun-facing hemisphere. Loewy and his collaborator Eugene Quito emphasized that the geometry at the HST observation epoch placed Earth only about 10 degrees away from the Sun, divided by 3I Atlas line, meaning we were viewing the object nearly edge on the sunward extension they measured, stretched approximately 10 times longer than its width, implying a highly elongated structure when corrected for projection effects. This is unusual but not unprecedented in the comet literature. Some comets show strongly anisotropic outgassing due to active regions concentrated on particular parts of the nucleus. What makes 3 Atlases' case interesting is the combination of sunward enhancement, the extreme aspect ratio, and the CO2-dominated chemistry that we're about to discuss. The carbon dioxide dominant coma is perhaps the most robustly established anomaly because it comes from JWST spectroscopy, the gold standard for compositional analysis. Near-infrared spectra acquired in late September showed CO2 emission lines dominating the spectrum with a CO2 to H2O ratio of approximately 8 ± 1. This is far higher than typical solar system comets where water usually dominates, and carbon dioxide contributes anywhere from a few percent to maybe 30% of the volatile budget. High CO2 objects exist in the solar system. Comet 29P divided by ʻOumuamua. ʻOumuamua 1 is famous for its CO2-driven outbursts, but they're rare. The high ratio suggests that 3-2 Atlas formed in an environment where CO2 remained frozen while water ice was depleted, either because it formed beyond the CO2 ice line in its parent system, or because surface processing by cosmic rays and UV photons preferentially removed water over geological timescales. Both scenarios are physically plausible, but they place constraints on the object's origin and history that are difficult to verify without knowing which stellar system it came from and when it was ejected. The nickel-rich iron-weak composition is where Lowe's framing becomes most aggressive and most controversial. His medium essay titled "Extreme Nickel Production" highlighted spectroscopic detections of neutral nickel emission lines across a range of heliocentric distances, from approximately 3.14 astronomical units inward to 2.14 AU. Iron emission, typically seen alongside nickel in cometary spectra, was absent below approximately 2.64 AU. Lowe interpreted this as implying anomalously high nickel-to-iron ratios in the outgassing material, calling it extreme and exceptional compared to solar system comets and 2I divided by Boris. Neutral nickel and iron emission from comets is itself a relatively recent discovery, with the first detections published only in the last decade. The presence of these metal atoms in cometary atmospheres is puzzling because vaporizing refractory metals requires high temperatures well above what typical ices reach, even near perihelion. The leading explanation invokes photodissociation of organometallic molecules or sublimation of metal-bearing grains heated by solar radiation. But why nickel would dominate over iron in 3 Atlas's coma, given that iron is more abundant in typical cosmic chemistry, is unclear. Lowe's claim is that the ratio behavior is unusual enough to warrant consideration of non-natural origins, specifically industrial alloys, where nickel is deliberately enriched. This is speculation stacked on top of incomplete data, but it's not pulled from thin air. The spectroscopic measurements are real, even if their interpretation is debated. Extreme negative polarization enters more specialized territory. Polarimetry measures how much light from an object is linearly polarized, meaning the electric field oscillates preferentially in one direction rather than randomly. Comets polarize sunlight through scattering off dust grains, and the polarization depends on grain size, shape, composition, and viewing geometry. Polarization as a function of phase angle, the angle between sun, comet, and observer, follows characteristic curves that allow astronomers to classify comets into families. 3. Io Atlas's polarimetric curve, measured across multiple phase angles during its approach, showed parameters distinct from known solar system comet families. Specifically, it exhibited more negative polarization at small phase angles than typical comets, though still within ranges that natural dust grain models can reproduce if you allow for unusual grain properties. The polar imagery preprint that reported these measurements framed them as expanding the known diversity of cometary dust rather than implying artificial origins. But diversity has limits. If every interstellar object we detect falls outside the range established by thousands of solar system comets, At some point, we have to ask whether expanding diversity is doing too much explanatory work. The brightness versus acceleration tension is more subtle and requires understanding how non-gravitational forces affect comet orbits. When a comet outgasses, the expelled gas and dust carry momentum if outgassing is anotropic, concentrated on one hemisphere or in specific jet directions. The reaction force acts like a tiny rocket thruster, pushing the comet slightly off a pure Caprian orbit. This non-gravitational acceleration scales inversely, with mass for a given outgassing rate. Small comets experience larger deviations from gravitational trajectories than large comets with the same activity level. By measuring the non-gravitational acceleration and estimating outgassing rates from coma brightness, you can constrain the comet's mass and therefore its size if you assume a density. 3 Atlas shows relatively weak non-gravitational acceleration given its brightness, which, in Lowe's analysis, implies high mass. High mass means either large size or unusually high density. Loeb opts for large size, arriving at his 5 kilometers diameter estimate. Critics argue that the relationship between coma brightness and nucleus mass is uncertain because brightness depends on dust production, which doesn't directly constrain the volatile content or total mass of the nucleus. The tension exists, but its resolution depends on which uncertainties you're willing to accept and which assumptions you prioritize. 7 anomalies, each one individually explainable within the framework of natural processes if you allow for exotic formation conditions. Unusual compositions, or rare but plausible geometries. Ecliptic alignment could be chance. Planetary encounter timing could be selection bias. Sunward glow could be anotropic outgassing viewed edge-on. CO2 dominance could be formation near a CO2 ice line or radiation processing. Nickel to iron behavior could be unusual grain photochemistry. Negative polarization could be expanding the natural diversity of dust properties. Weak acceleration, despite brightness, could be high mass or uncertain dust-to-gas ratios. None of these explanations are implausible on their own. But when you require every single one to be true simultaneously in the same object, you're stacking coincidences into a tower that starts to look precarious. Lowe's rhetorical strategy is to emphasize that tower, to argue that the conjunction of anomalies strains the natural hypothesis beyond what Occam's razor comfortably allows. Mainstream astronomers push back by noting that our sample size is 3 interstellar objects total. That diversity in nature is vast, and that extraordinary claims require extraordinary evidence. Both positions are defensible, which is why 3I Atlas has become such a flashpoint in the ongoing debate about how we interpret ambiguous data. The nickel problem deserves its own deep dive, because it's the anomaly that most directly invokes industrial or engineered chemistry. If you're looking for smoking gun evidence that 3 Atlas might not be natural, the metal emission ratios are where you'd focus your attention. And that's exactly what we're going to do next. Because the chemistry of this object is not just strange, it's diagnostic. Part 8. The nickel problem. Nickel without iron echoes the elemental signatures of industrial stainless steel alloys, where nickel is deliberately added to enhance corrosion resistance and mechanical properties. That comparison is Avi stated explicitly in his Medium essays and picked up by outlets like The Debrief in their coverage of 3 Atlas observations. It's a provocative framing, and it demands that we separate what the observations actually show from what they might imply. Lowe's extreme nickel production essay summarized spectroscopic detections spanning 3 Atlas's inbound trajectory from approximately 3.14 astronomical units, where observations first detected neutral nickel emission, down to 2.14 AU, as the object approached perihelion. Nickel appeared consistently across this range, showing up as characteristic emission lines in the visible spectrum around 5,000 to 6,000 angstroms. These lines result when neutral nickel atoms in the coma absorb solar ultraviolet photons and remit visible light at specific wavelengths determined by nickel's atomic structure. Iron, which has its own set of emission lines in similar wavelength regions, was absent from spectra obtained below approximately 2.64 AU. The implication is that either iron was never present in significant quantities in the outgassing material, or that iron and nickel are being produced or released by different mechanisms that activate at different heliocentric distances. Let's ground the puzzle in accessible chemistry at the heliocentric distances we're discussing. Solar heating drives surface temperatures on a comet nucleus to somewhere between 200 and 300 Kelvin, depending on albedo and thermal inertia. Those temperatures are sufficient to sublimate water ice, carbon dioxide ice, carbon monoxide ice, and various other volatile ices that comprise cometary nuclei, but they're nowhere near sufficient to vaporize metallic nickel or iron directly. Nickel melts at 1,728 Kelvin. Iron melts at 1,811 Kelvin. Vaporization temperatures are even higher. So when we see neutral nickel and iron atoms in cometary atmospheres, they're not coming from bulk metal vaporizing off the nuclear surface. Instead, they likely originate from organic, metallic molecules, metal atoms, bonded into organic structures, or from small dust grains containing metal phases that are heated to much higher temperatures than the bulk nucleus by solar radiation absorption. The discovery of nickel and iron emission from comets is relatively recent, first reported convincingly in 2019 from observations of Interstellar Comet 2 is divided by Boris, and subsequently confirmed in several solar system comets before these detections. The conventional wisdom held that refractory metals shouldn't appear in cometary coma because the temperatures were too low. The discoveries forced a rethinking of cometary chemistry and opened questions about metal delivery mechanisms that are still being actively debated in the literature. Most models invoke photodissociation of molecules like nickel, carbonyl, or iron carbonyl, which can sublime at much lower temperatures than the pure metals and then break apart in sunlight to release metal atoms. Another possibility is that submicron grains containing metal phases get heated to very high temperatures by absorbing concentrated solar flux, reaching thermal equilibrium temperatures that allow metal sublimation from grain surfaces. What makes 3 Atlas's behavior noteworthy is not the presence of nickel, which has now been seen in other comets, but the ratio of nickel to iron and how that ratio evolves with heliocentric distance, cosmic abundances. The relative amounts of elements produced by stellar nuclear synthesis and found throughout the universe show iron outnumbering nickel by a factor of roughly 17 to 1. Iron is the most abundant heavy element in the universe, after oxygen, silicon, magnesium, and a few others. Nickel is relatively common, but distinctly less so than iron. Solar system materials generally reflect cosmic abundances unless specific processes have fractionated them. Meteorites, which sample the solid materials that built planets and asteroids, show iron to nickel ratios broadly consistent with cosmic values. Comets, being primitive bodies that formed in the cold outer regions of the protoplanetary disk, should also reflect cosmic or near-cosmic metal ratios in their composition. If 3 Atlas shows nickel without iron or nickel in great excess compared to iron, several possibilities emerge. 1. The parent material that formed the comet was chemically fractionated in ways that enriched nickel relative to iron. This could happen if the formation environment preferentially condensed nickel-bearing phases, while leaving iron and gas or other phases that didn't accrete into the nucleus. 2. The mechanisms releasing metal atoms into the coma operate differently for nickel and iron, perhaps because they're bonded into different molecular carriers or grain phases that sublime or photodissociate at different temperatures or solar flux levels. 3. Observational selection effects make nickel easier to detect than iron in the wavelength ranges and sensitivities of the spectrographs being used, creating an apparent abundance anomaly that doesn't reflect the actual composition. Or 4. The material is not natural cometary composition, but instead reflects processing or engineering that deliberately altered metal ratios. Low frames option 4 frames as a viable hypothesis pointing to terrestrial industrial alloys where nickel is added to iron to create stainless steels, superalloys, and other materials with enhanced properties. He's not claiming that 3 Atlas is made of stainless steel welded together in some alien factory. His argument is more subtle. If the object were an engineered structure designed to survive interstellar travel and close solar approaches, its exterior might be coated or constructed from materials chosen for thermal stability, radiation resistance, and mechanical strength. Such materials might have nickel-to-iron ratios that differ from cosmic abundances because they were optimized for performance, rather than reflecting the natural elemental distribution of their source environment. When such materials ablate or outgas under solar heating, the released atoms would carry the engineered ratios into the coma, where spectroscopy would detect them as anomalous compared to natural expectations. This is speculation clearly labeled as such, but it's testable speculation. If 3 Atlas continues to show nickel-rich emission as it rounds perihelion and begins its outbound journey, and if higher signal-to-noise spectroscopy confirms that iron remains absent or subdominant, the case for unusual composition strengthens. If future observations detect iron appearing at different heliocentric distances or phase angles that would support the interpretation that nickel and iron come from different carrier phases with different temperature thresholds, if laboratory studies of analog materials, organometallics, or metal-bearing grains subjected to UV photosis and thermal cycling can reproduce the observed emission patterns that would provide a natural pathway, the data are not yet conclusive, which is why Lowe's exceptional framing coexist with mainstream caution. There's a tie-in here to Lowe's earlier work on M1, the interstellar meteor that his team retrieved debris from in the Pacific Ocean floor. Analysis of metallic spherules recovered during that expedition claimed to find unusual elemental ratios and isotopic signatures that Lowe interpreted as evidence of artificial origin, or at least non-solar system provenance. Independent laboratories that examined similar spherules disputed those interpretations, arguing that the ratios were consistent with terrestrial contamination or misidentified cosmic spherules formed from natural meteoroid ablation. The controversy over IM-1 findings has made some in the community skeptical of Lowe's claims about 3I Atlas's nickel behavior, viewing it as part of a pattern where he finds industrial signatures in data that others interpret as natural variants. That skepticism is fair, but it doesn't invalidate the spectroscopic measurements themselves, which come from established observatories and are published or pre-printed for community scrutiny. What future observations could resolve the nickel problem? Higher signal-to-noise spectra across a wider range of heliocentric distances and phase angles would help establish whether the nickel-to-iron ratio is truly constant or varies with observing geometry. Multi-wavelength coverage, including ultraviolet spectra, could detect iron emission lines that might be too weak to see in visible light observations. Laboratory measurements of metal emission from cometary analog materials under controlled conditions would calibrate what ratios to expect from natural processes, and comparative studies of other comets, both solar system and interstellar, if we get lucky enough to detect more, would establish whether 3 Atlas's behavior is unique or part of a broader population of nickel-rich objects. None of these observations have been completed yet, which means the nickel problem remains open, unsolved, and provocative. The spectroscopic weirdness combines with morphological weirdness to create a composite picture that's harder to explain than either anomaly alone. The nickel problem tells us something is chemically unusual about what's coming off this object. The sunward jet tells us something is geometrically unusual about how material is being released and distributed. Together they point toward either exotic physics we don't fully understand, or engineering we're not yet willing to seriously consider. The sunward jet and its implications are where we turn next. Because that morphology is not just strange, it's directional. And directionality in nature usually requires either strong selection pressures or deliberate design. Part 9. The sun-facing jet and the shadow tail. Hubble Space Telescope captured 3 Atlas during mid-September 2025, producing images that would fuel months of speculation and analysis. The morphology was immediately striking to anyone familiar with typical cometary appearances. Dust and gas elongated preferentially toward the sun, creating what astronomers call an anti-tail, a forward-pointing structure opposite to the classic anti-Euler tail that defines the iconic comet silhouette. The sunward extension measured approximately 10 times longer than its width in the Hubble images, an extreme aspect ratio that implied either a highly collimated jet pointing directly at the sun or an extended dust trail viewed nearly edge-on from Earth's vantage. The geometry matters for interpreting what we're seeing. At the epoch of Hubble's observations, the Sun, Earth, and 3E Atlas formed a configuration where Earth lay only about 10 degrees away from the Sun divided by comet line. This means we were viewing the object almost directly along the sun-facing axis, seeing any sunward structure in its most elongated projection. If the object had a symmetric coma, we'd expect to see a roughly circular or elliptical envelope with perhaps a slight elongation due to dust tail formation. Instead, Hubble saw a pronounced needle pointing at the sun with a much weaker and shorter antis-Euler tail trailing behind. Lowe and his collaborator Eugene Quito modeled this geometry in their analysis, noting that the true three-dimensional extent of the sunward feature is likely even longer than the 10:1 aspect ratio suggests, because we're viewing it somewhat foreshortened, even at 10 degrees off axis. Anti-tails are not unprecedented in solar system comets. They occur when we view a comet's orbital dust trail edge-on, so that particles released earlier in the comet's orbit appear projected in front of the nucleus from our line of sight, even though they're physically trailing behind along the orbital path. Classic examples include Comet Erin-Rowland in 1957, which displayed a prominent spike appearing to point toward the sun, due purely to viewing geometry of its dust trail. The difference with 3 Atlas is that the anti-tail's extreme aspect ratio and brightness relative to the anti-solar tail suggests more than just geometric projection. The modeling in the Hubble analysis paper invoked anotropic emission from a hot dayside hemisphere, with dust and gas preferentially released from regions directly illuminated by the sunday. This would create a real physical concentration of material on the sunward side, not just an apparent concentration due to viewing angle. Anotropic outgassing is common in comets, because nuclei are not uniform spheres with symmetric activity. Active regions, patches of exposed volatile ice, or areas with different thermal properties can concentrate jets in specific directions. The nucleus rotation carries these active regions through day and night cycles, modulating the outgassing pattern. But most comets show multiple jets at various angles, not a single dominant sunward concentration. The physics of why 3 Atlas would preferentially outgas directly toward the Sun, sustaining that pattern over weeks of observation, requires either a very specific nuclear shape and rotation state, or a surface composition where sunward F-facing areas have fundamentally different volatile content than other regions. Both are possible within natural framework, but both push against the central tendency of how comets typically behave. Speculative mechanical analogies start to intrude here, and they need to be clearly marked as such because we're venturing into territory where physics and imagination blur. If 3 Atlas possessed a reflective surface rather than an absorptive, dusty one, sunlight hitting the day side would bounce back toward the Sun, rather than being absorbed and re-radiated thermally. This specular reflection could create a concentrated brightness enhancement along the Sun-facing direction, appearing in images as a bright jet, even though no material is actually being expelled. Think of it like a solar sail, where flat reflective panels scatter sunlight preferentially in directions determined by surface orientation. The analogy breaks down quickly because solar sails are engineered to be flat and highly reflective, while natural bodies tend to be rough and dark. But the principle illustrates how surface properties can create directional optical effects that might masquerade as jets in imaging data. Another speculative analogy invokes radiation pressure plumes, resembling ion drive exhaust. Ion thrusters used on spacecraft for high-efficiency propulsion work by accelerating charged particles and expelling them at high velocity. The exhaust plume from an ion engine is highly collimated, creating a narrow beam of material extending behind the spacecraft. If 3-2 Atlas was somehow generating a plume of charged particles or ionized gas directed sunward, perhaps as a byproduct of electrical charging in the solar wind or some kind of active emission system, that plume could appear as a bright sunward extension in optical images. The physics required for this scenario are entirely speculative, and there's no known natural mechanism that would create a sustained sunward ion beam from a comet. But if we're entertaining artificial hypothesis, directed emission of some kind becomes at least conceptually possible. A third speculative frame considers directional outgassing designed for thermal control. Engineered spacecraft manage heat by using radiators, surfaces deliberately oriented to radiate thermal energy into cold space. If 3-2 Atlas were a structure designed to survive close solar approach, it might employ outgassing or sublimation of surface materials as an active cooling mechanism, with emission directed preferentially sunward to maximize cooling efficiency. This would be a form of ablative heat shielding, where material boiling off the sun-facing side carries away thermal energy and prevents the interior from overheating. The chemistry would matter enormously. Carbon dioxide sublimation, which JWST confirmed as the dominant volatile, is an excellent coolant because it has high latent heat of sublimation. Using carbon dioxide as an engineered thermal management fluid is not absurd from a physics standpoint, though claiming 3-IO Atlas employs engineered thermal control is a massive leap beyond available evidence. Natural explanations for the antiel exist and have been published. A recent preprint appearing on ARIP in late September 2025 modeled 3E Atlas's sunward morphology using anotropic survival radius of sublimating ice grains. The basic idea is that dust grains released from the nucleus contain embedded ice that continues sublimating as the grains move through the coma. Grains heading sunward experience stronger solar heating and sublimate more rapidly, creating a population of grains that survive longer in anti-polar directions than in sunward directions. This differential survival can produce an apparent sunward concentration of smaller grains or gas, while larger grains that resist sublimation create the classic anti-solar dust tail. The model reproduces 3I Atlas's observed morphology without invoking artificial structures or exotic physics. It's a natural explanation that expands our understanding of cometary dust dynamics rather than challenging the fundamental assumption that we're looking at a comet. The question becomes, which explanation is more economical? Natural anotropic processes that are complex but plausible within established physics, or artificial structures that are conceptually simple but require abandoning the default assumption that interstellar visitors are natural bodies. Occam's razor, the principle that simpler explanations are preferable, doesn't straightforwardly favor one over the other, because simplicity depends on your prior. If you start with the assumption that interstellar objects are always natural, then even complex natural models are simpler than invoking engineering, because they don't require the extraordinary claim that artificial objects traverse interstellar space. If you start agnostic about interstellar object origins, then a simple engineered explanation might be more economical than stacking multiple exotic natural processes. LOE operates from the agnostic prior. Mainstream astronomy operates from the natural prior. Neither position is inherently wrong, but they lead to very different interpretations of ambiguous data. What new observations would distinguish engineered from natural interpretations of the sunward morphology? Variability patterns offer one diagnostic. If the sunward jet is tied to nucleus rotation, we should see periodic modulation as active regions rotate into and out of sunlight. Natural jets typically show rotational modulation with periods ranging from hours to days, depending on nucleus size and spin rate. If 3I Atlas's sunward feature remains steady in brightness and morphology over time, scales longer than plausible rotation periods, that would be unusual and potentially diagnostic of a non-rotational mechanism. High-resolution imaging that resolves the nucleus and near-nucleus jets would show whether emission comes from discrete, active areas or from a more uniform dayside release. Polarization maps could distinguish between scattered sunlight from dust grains and specular reflection from smooth surfaces. And spectroscopic monitoring of the sunward feature versus the antisolar tail could reveal compositional differences that would inform whether we're seeing different grain populations or different physical mechanisms. None of these observations have been completed at high enough resolution and cadence to definitively resolve the question. Hubble provided morphology, but not high-time resolution variability. JWST provided composition, but not resolved imaging of the nucleus. Ground-based spectroscopy provided metal emission detections, but not spatially resolved maps of where those emissions originate. The Mars flyby potentially offered close vantage points from orbiters that could have added crucial pieces. But, as we discussed in Act 1, those data either haven't been acquired, haven't been released, or haven't been processed with sufficient priority to appear in public archives yet. The sunward jet remains an open question, beautiful in imaging, suggestive in its geometry, but ultimately ambiguous in its origin. That ambiguity sits at the heart of why 3I Atlas has captured public imagination in ways that two divided by Boris never did. Borisov was weird in composition, showing chemical signatures distinct from solar system comets, but its morphology was boringly normal. It looked like a comet. It behaved like a comet. 3 Atlas looks like something trying to be a comet, but not quite succeeding. The sun would jet the blue smudge from Mars, the nickel without iron, the near-ecliptic trajectory. All of these elements combine into a gestalt that feels off, even if you can't precisely articulate why. And in that felt wrongness in the gap between what we expect and what we observe, a narrative space opens for speculation that would be immediately dismissed if the observations were more mundane. We've now surveyed the object itself, its orbit, its chemistry, its morphology. We've laid out 7 anomalies and explored how each might be natural, artificial, or some combination we haven't yet imagined. But there's one more element of the story that we haven't adequately addressed, and it's the element that transforms scientific curiosity into something darker and more conspiratorial: the silence. The gap between what observers expected and what agencies delivered. The perception, right or wrong, that information is being withheld, massaged, or delayed for reasons beyond normal scientific caution. That perception and the fertile ground it creates for speculation about cover-ups and hidden truths is what we confront next. Because if 3 Atlas is genuinely unusual, the question isn't just what it is. The question is who gets to control the story of its discovery, and what happens when that control slips. Part 10. The Cover-Up in Plain Sight. A-Vibe set expectations in his pre-fly medium essays with crisp specificity. The Mars Reconnaissance Orbiter's high-rise camera could provide diameter constraints at approximately 30 kilometers per pixel effective resolution. ES Mars Express and the ExoMars Trace Gas Orbiter could contribute spectroscopy across infrared wavelengths. Perseverance's Mastcam-Z and other instruments could capture night sky observations if mission planners allocated time. The observation window spanned October 1st through 7th, bracketing the October 3rd closest approach. Multiple independent platforms, multiple viewing geometries, multiple spectroscopic capabilities, all trained on a target that had been tracked and predicted for months. The community waited for a data bonanza. What arrived instead was a trickle, and then the leaked stack that bypassed official channels entirely. Public feeds from NASA's Mars missions stayed quiet in the immediate aftermath of closest approach. The usual daily or near-daily updates of raw images from Perseverance continued, but they showed rocks, wheel tracks, and Martian landscapes. No obvious night sky frames featuring a faint interstellar visitor. No press releases announcing detection or non-detection. No curated image galleries with carefully processed composites showing 3 Atlas against the Martian sky. The Hire's archive, searchable by observation ID and target coordinates, showed no new entries corresponding to 3I Atlas during the flyby window, at least not in the publicly accessible catalog that amateur researchers could query. Mars Express data feeds remained technical and unlabeled in ways that made searching for specific targets difficult without insider knowledge of observation planning. ExoMars TGO, the youngest of the Mars orbiters and still relatively new to science operations, maintained its focus on atmospheric trace gas measurements, with no public indication that it had attempted interstellar object observations. The silence could be explained entirely within the framework of normal mission operations. And we need to be fair about this, even as we explore why silence feels louder than neutral. Data analysis takes time, particularly for off-nominal observations that weren't part of the original mission plan. Mars orbiters and rovers have primary objectives related to Martian science, geology, atmosphere, climate, astrobiology, resource characterization for future human missions. Observing a transient interstellar visitor is a bonus, a target of opportunity that gets scheduled if time and spacecraft pointing allow, but it doesn't take precedence over core objectives. When data come down from such bonus observations, they enter processing queues behind higher priority datasets. Calibration requires matching instrument pointing with precise ephemerides for the target, which means waiting for updated orbital solutions from observers tracking 3 Atlas from Earth. Quality assurance requires checking for instrumental artifacts, cosmic ray hits, and processing errors before declaring a detection or non-detection. All of this takes days to weeks, not hours. But the temporal gap between expectation and delivery creates fertile ground for alternative narratives. The US government shutdown that began September 30th and affected some NASA operations became a convenient explanatory hook. Even though shutdowns don't halt deep space mission operations or data collection, public affairs offices scale back during shutdowns. Press releases get delayed. Non-critical personnel are furloughed, which can slow the human-intensive process of curating data for public release. But spacecraft keep operating. Telemetry keeps flowing to ground stations. Mission-critical analysis continues. The shutdown affected communication more than capability, but in a story already primed for conspiracy thinking, communication delays looked like deliberate suppression, regardless of their actual cause. The diffusion loop that amplified Schmaus's leaked mass cam Z stack also amplified narratives about agency silence. Blue Skak's threads filled with speculation about why official data weren't appearing. Reddit communities debated whether Mars orbiters had actually observed the target at all, or whether observation plans had been quietly cancelled. YouTube creators produced videos with titles asking whether NASA was hiding evidence of an interstellar probe, using the genuine lack of public data releases as supporting evidence for cover-up hypothesis. The Debrief and similar outlets published articles that carefully walk the line between reporting on community speculation and endorsing it, giving platforms to the questions without necessarily claiming answers. Each amplification cycle added distance from the technical reality of normal data processing timelines, constructing a social reality where silence equaled malfeasance. Historical analogies temper the suspicion, while also feeding it. ʻOumuamua's discovery, in October 2017, was followed by months of ambiguity about its nature, composition, and origin. Initial observations showed an elongated light curve, consistent with a tumbling, highly elongated object. Subsequent astrometry revealed non-gravitational acceleration that couldn't be explained by typical cometary outgassing because no coma was detected. Lowe's published hypothesis that ʻOumuamua might be an artificial light sail emerged in 2018, sparking heated debates that continue to this day. Throughout that period, data releases were slow, analysis was contested, and the gap between initial detection and scientific consensus allowed speculation to flourish. The ambiguity was real, but it resulted from observational limitations and genuine scientific uncertainty, not from institutional suppression. In one followed a similar trajectory. The interstellar meteor detection from US government sensors, declassified and analyzed by Lowe's team, led to an ocean floor retrieval expedition that claimed to recover metallic spirals of possible interstellar origin. Those claims faced immediate pushback from researchers who argued the spherules were terrestrial contamination or misidentified cosmic spherules from ordinary meteoroids. Laboratory analyses disagreed on isotopic ratios and elemental compositions. Lowe maintained that his team's findings supported artificial, or at least anomalous, origins. Critics maintained that the data were consistent with natural explanations, and that extraordinary claims were being built on ordinary measurements. The controversy remains unresolved, but it established a pattern where Lowe's public essays preceded formal peer review, where institutional scientists pushed back against interpretations they viewed as speculative, and where the public watched day. Scientific dispute play out in real time, through Medium posts and asks of preprints rather than waiting for journal publication. 3 Atlas fits this pattern perfectly. Lowe's essays stack anomalies and frame questions before agencies issue official statements. Ambiguous observations, like the leaked Mars stack, bypass verification pipelines and achieve viral circulation. Institutional silence, whether due to caution, processing delays, or shutdown logistics, gets interpreted as evidence rather than absence. The public narrative runs ahead of the scientific one, creating expectations that agencies then struggle to meet because their timelines are measured in weeks. While social media operates in hours, is there any scenario where agencies would genuinely withhold data that showed something extraordinary? The question itself is conspiratorial, but it's worth considering seriously because the answer informs how we interpret silence. If initial imaging from HiRISE or Mars Express showed morphology that was clearly inconsistent with a natural comet, sharp edges or regular geometric patterns or reflectivity that implied machine surfaces, would agencies immediately release that data to the public? Or would they internally review, consult with experts, check for instrumental artifacts, and potentially coordinate with other agencies before making any statement? The cautious answer is that extraordinary data would receive extraordinary scrutiny before release, not because of a cover-up instinct, but because the consequences of being wrong are enormous in both directions. Prematurely announcing artificial origin for something that turns out to be a natural comet with unusual properties damages credibility and fuels conspiracy theories. Prematurely dismissing anomalous features as artifacts, when their real delays scientific understanding and potentially hides information of profound importance. The most likely scenario is the boring one. Mars assets did observe 3 Atlas during the flyby window. Some observations succeeded, others failed due to pointing errors or unfavorable lighting conditions. The successful observations are being processed through normal pipelines by analysts juggling multiple projects and operating under budget and time constraints. Preliminary results are being checked against models, compared with Earth-based observations, and prepared for eventual publication through peer-reviewed channels. The timeline for this process is weeks to months, not days. When results appear, they'll probably show that 3 Atlas is consistent with an exotic but natural comet, expanding our understanding of interstellar object diversity without requiring artificial hypothesis. The leaked MASCAM-Z stack will be explained as a processing artifact, misregistration, or at best, a marginal detection of diffuse coma that doesn't add significant new information beyond what JWST and Hubble already provided. But the boring scenario doesn't satisfy anyone emotionally invested in the mystery. It doesn't explain why Schmaus's stack showed blue when everything else showed green or neutral. It doesn't address the conjunction of 7 anomalies that Lowe has catalogued. It doesn't resolve the felt wrongness that many observers experience when looking at 3 Atlas's data composite. And it doesn't account for the remote but non-zero possibility that we're actually looking at something artificial, that the silence is genuine caution in the face of paradigm-shattering discovery, and that the leaked image represents not an artifact, but a glimpse of truth escaping through the cracks of institutional control. We're at a decision point in the narrative. Act 2 has laid out the object and its oddities, the orbital precision, the chemical strangeness, the morphological peculiarities, and the information dynamics that surround it. Act 3 must confront implications. If 3I Atlas is just an exotic comet, what does it teach us about interstellar space and planetary system formation? If it's something more, something engineered or intentionally delivered, what does that mean for our understanding of intelligence in the universe and our place within the cosmic ecosystem? And how do we, as individuals without access to classified data or insider knowledge, navigate the gap between what we're told and what we suspect? Those questions are where we go next, because the smudge from Mars, real or artifact, has already changed the conversation. It's made the unthinkable thinkable. And once that threshold is crossed, there's no simple way back. Part 11. Mars, the silent witness. If the leaked stack is genuine, if Perseverance's Mars CAM-Z truly captured 3 Atlas transiting the Martian night, then Mars itself becomes the most important witness to this entire event. Not because Mars is special astronomically, but because Mars offers verification pathways that Earth-based observations cannot match. Distance matters, geometry matters, and most critically, control over the narrative matters. When you're dealing with claims that challenge fundamental assumptions about what moves between the stars, secondary corroboration paths exist and are straightforward to enumerate, even if accessing them proves difficult. Mars orbiters, particularly the Mars Reconnaissance Orbiter with its high-rise camera, observed from vantage points much closer to 3I Atlas during the October 3rd flyby than any Earth-based telescope. 29 million km separates Mars from 3I Atlas at closest approach. 150 million kilometers separates Earth from Mars at this point in both planets' orbits. Add in the changing geometry as 3I Atlas moved through the inner solar system, and Mars-based observations potentially offered spatial resolution and brightness sensitivity that Earth could not match. If HiRISE imaged the target successfully, the data should show either a point source, an extended coma, or nothing, depending on the object's true nature and brightness. Point source would suggest compact structure. Extended coma would confirm the natural comet hypothesis. Nothing would indicate the object was fainter than predicted or that pointing errors prevented detection. Spectroscopy from Mars orbiters adds compositional constraints. Mars Express carries Omega, a visible and infrared mineralogical mapping spectrometer that in principle could have captured 3 Atlas spectra if the observation was planned and executed. ExoMars Trace Gas Orbiter's instruments designed for atmospheric analysis are less suited for point source spectroscopy, but might have attempted measurements during the flyby window. These observations would complement JWST's compositional findings, potentially revealing differences in coma chemistry, as seen from Mars's closer vantage point. If the carbon dioxide to water ratio changed with viewing geometry, or if metal emission lines showed different relative intensities from Mars versus Earth, that would inform models of coma structure and outgassing mechanisms. Perseverance itself would have attempted repeat observations after the initial leaked stack. The rover operates autonomously between command uploads, but mission planners can schedule sequences days in advance. If the October 4th stack genuinely detected 3 Atlas, planners could have commanded additional night sky imaging sessions on subsequent nights to track the object's motion and confirm the detection. The fact that no subsequent stacks appeared publicly suggests either that follow-up observations weren't commanded, that they were commanded but failed, or that they succeeded and are being held for coordinated release. Each possibility carries implications. No follow-up suggests either that mission planners didn't trust the initial detection or that rover resources were prioritized elsewhere. Failed follow-up suggests marginal detection thresholds, where success depends sensitively on atmospheric conditions and pointing precision. Successful follow-up held for coordinated release suggests that agencies are treating this as a significant finding. Requiring careful presentation, the agency rolls around the October 1st through 7th observation window were multinational and multifaceted, at least in principle. NASA operates Mars Reconnaissance Orbiter and Perseverance. ESA operates Mars Express and ExoMars TGO. Data sharing agreements between space agencies mean that significant findings from one mission are typically communicated to others, allowing coordinated observation campaigns and cross-verification. If NASA's assets detected something unusual during the 3I Atlas flyby, ESA would likely have been informed and could have contributed independent observations or analysis. The multinational character of Mars exploration means that a coordinated suppression scenario requires conspiracy across agencies, cultures, and bureaucratic structures that don't naturally align. This doesn't make coordination impossible, but it raises the bar for what would be required to maintain operational silence across multiple independent organizations. Shutdown optics plus high-stakes claims create a perfect rumor ecosystem, and we're living in the middle of it. When the US government shutdown coincided with the Mars flyby window, it provided a ready-made explanation for why NASA's public communication channels went quiet. But shutdowns don't affect ESA operations. Mars Express and ExoMar TGO continued operating normally. Their data continued being collected and archived, and their science teams in Europe faced no shutdown-related constraints. If European assets detected something extraordinary, there would be no shutdown-related reason to delay announcement. The fact that no ESA announcement appeared suggests either that European observations didn't succeed, didn't show anything unusual, or are being held for the same reasons that might explain NASA's silence. The multinational silence is more challenging to explain with simple shutdown logistics, which feeds speculation that the reasons for delay transcend bureaucratic convenience. Geometry provides Mars a unique advantage that Earth-based telescopes lack. Atlas's trajectory brought it across Mars's forward hemisphere during the flyby, meaning Mars sat along a favorable sightline for observing the object's leading face, the hemisphere, oriented in the direction of motion through space. Earth's viewing geometry placed us more toward the side or trailing hemisphere, depending on the exact date. This difference matters if 3 Atlas has hemispherical asymmetries in brightness, composition, or structure. A reflective leading face or concentrated outgassing from the ram direction would appear brightest from Mars's vantage. Earth-based observers would see a different aspect. The lack of coordination between Mars-based and Earth-based apparent brightness or color could itself be diagnostic, revealing structure and asymmetry that would be invisible if we only had a single viewing geometry. What would count as a smoking gun from Mars assets? The list is short but clear. Coherent motion over multiple frames would confirm that the stack detection represents a real astronomical source rather than instrumental artifact, because artifacts don't move predictably across the sky. Spectroscopic lines matching JWST's carbon dioxide-rich coma would verify compositional consistency and support the natural comet hypothesis. Spectroscopic lines not matching JWST, particularly if they showed metal emission or absorption features inconsistent with cometary chemistry, would demand exotic explanations. Brightness profiles inconsistent with extended diffuse coma, particularly if they showed compact sources or structured light distributions, would challenge natural models. And chromatic consistency, or inconsistency with the blue smudge measured through multiband photometry rather than processed RGB stacks, would resolve whether the color anomaly is real or artifactual. None of these smoking guns have appeared in public data releases as of early October 2025. That absence is the silence that fuels speculation. We're left in a state of ambiguity, where the leaked stack exists as a social fact, circulated and debated across communities, but not verified or refuted by additional data that would settle the question. The ambiguity is sustainable for weeks, possibly months, until either agencies release Mars flyby results or attention moves onto other controversies. But for those paying attention, for those who followed ʻOumuamua's ambiguities and in one's disputes, the pattern is familiar and frustrating. Important questions hang unanswered, not because data don't exist, but because data pipelines and institutional caution create temporal gaps that speculation rushes to fill. Mars stands as the silent witness, its orbiters and rovers potentially holding information that would resolve debates or deepen mysteries. That information exists somewhere in telemetry streams and archive servers, waiting for human analysis and interpretation. Whether it emerges in days, weeks, or months depends on priorities we can't see and decisions we're not party to. And in that gap between event and revelation, we construct narratives that may or may not survive contact with eventual data. The leaked smudge has already shaped those narratives, transforming 3I Atlas from an interesting interstellar comet into a Rorschach test, where believers see confirmation and skeptics see artifacts. And both sides marshal Mars's silence as evidence for their positions. We need to step back now and connect 3 Atlas to the broader pattern that began with ʻOumuamua and continued through ʻOumuamua. Because if 3I Atlas is just the latest in a series of interstellar visitors that don't quite fit our expectations, then either our expectations are badly calibrated, or we're witnessing the early stages of a revelation that will reshape how we understand our place in the cosmos. That pattern, and what it might mean, is where we turn next. Part 12. From ʻOumuamua to Atlas, a pattern emerges. 3 data points do not make a trend, but they're enough to start asking whether we're seeing statistical noise or the first hints of signal. 1 ice divided by ʻOumuamua arrived in October 2017, the first confirmed interstellar object detected passing through our solar system. Its discovery was accidental, caught by the Pan-STARRS Survey telescope in Hawaii as a faint point of light moving against the background stars. Initial observations suggested an asteroid, a rocky body, without the gas and dust coma that defines comets. But its trajectory and subsequent non-gravitational acceleration didn't fit the asteroid hypothesis cleanly. The acceleration measured as a deviation from pure Caparian motion required either asymmetric outgassing like a comet or some other force acting on the object. No coma was detected even in deep imaging, which ruled out typical cometary outgassing. Lowe and his collaborator Shuel Bialy published a paper in 2018 proposing that the acceleration could be explained if ʻOumuamua were a light sail, a thin reflective sheet pushed by solar radiation pressure. The hypothesis was controversial, heavily criticized by most astronomers as unnecessary given that subtle outgassing from volatiles not producing visible coma could explain the acceleration. But the paper opened a door that subsequent observations have never quite closed. IM-1, Interstellar Meteor 1, entered the story through a different pathway. US government sensors designed to detect nuclear detonations recorded a meteor entering Earth's atmosphere over the Pacific Ocean in January 2014. The meteor's velocity and trajectory analyzed years later by Lowe's team using declassified data suggested interstellar origin based on its hyperbolic orbit. The material's strength, inferred from how the meteor broke apart during atmospheric entry, implied unusual composition, potentially metallic rather than typical stony or icy meteoroid material. Lowe organized and led an ocean floor expedition to the impact site, retrieving magnetic spherules from sediment that he claimed showed isotopic and elemental ratios inconsistent with solar system materials. Independent laboratories disputed those claims, arguing that the spherules were either terrestrial contamination, coal ash from shipping lanes, or ordinary cosmic spherules from non-interstellar meteoroids. The controversy remains unresolved, with Lowe maintaining that his team's findings support artificial, or at minimum anomalous, interstellar origin, while critics maintain that the data have been misinterpreted. 3. I-Atlas represents a dramatic escalation in data richness compared to its predecessors. MUA was discovered on its way out of the solar system, giving observers only weeks to gather data before it faded beyond detection limits. M1 was a single event lasting seconds, leaving only atmospheric entry signatures and recovered debris as evidence. 3.2 Atlas was discovered months before perihelion, allowing extended observational campaigns with flagship instruments. JWST spectroscopy provided compositional certainty that ʻOumuamua lacked. Hubble morphology revealed structure that ʻOumuamua's point source appearance couldn't show. Ground-based spectroscopy detected metal emissions that neither predecessor exhibited. The Mars flyby offered close approach opportunities that neither previous object provided. 3. Atlas is the most data-rich interstellar visitor we've studied, and yet, or perhaps because of that richness, it's also the most ambiguous in interpretation. The bundle of anomalies distinguishes 3 Atlas from typical solar system comets more dramatically than either predecessor deviated from their comparison populations. ʻOumuamua's weirdness was primarily dynamic. The non-gravitational acceleration without visible coma in one's weirdness was compositional, the inferred material strength and claimed isotopic anomalies. 3 Atlas combines dynamic, compositional and morphological oddities into a single package. The near-ecliptic trajectory, with multiple planetary encounters, echoes ʻOumuam's surprising approach geometry. The claimed unusual metal ratios echo one's disputed spheral chemistry. The sunward antitail and carbon dioxide-dominated coma add morphological and compositional elements that neither predecessor showed. The polarization measurements falling outside known comet families add phototrick oddities, and the potential Mars surface detection, if real, adds observational confirmation from a vantage point that transforms the entire narrative. Institutional reaction patterns have also evolved across the 3 objects. MMU generated initial excitement, followed by mainstream pushback against Lowe's light sail hypothesis, with most astronomers settling on exotic but natural explanations involving outgassing from volatiles like nitrogen or hydrogen. ICE. IM1 generated skepticism from the start, with many researchers questioning whether the meteor was genuinely interstellar and disputing the compositional claims from recovered spherules. 3 Atlas has generated a more complex reaction with robust mainstream science papers, characterizing it as an unusual but natural carbon dioxide-rich comet, while Lowe's parallel narrative frames it as potentially artificial or at minimum deserving serious consideration of that hypothesis. NASA and ESA press releases have emphasized the comet interpretation, highlighting JWST's compositional findings and explaining the sunward morphology through natural outgassing models. Media coverage has split between outlets emphasizing the mainstream comet story and others amplifying LOE's anomaly framing. The Guardian published an article in late September, explicitly pushing back against alien tech interpretations, quoting astronomers who argued that 3E Atlas's features are unusual but consistent with natural diversity in cometary populations. The article noted that carbon dioxide-rich comets exist in the solar system, that sunward anti-natural explanations, and that attributing anomalous features to artificial origin requires far stronger evidence than currently exists. This institutional reassurance, delivered through reputable journalistic channels, serves a function in the information ecosystem. It provides a counter-narrative to speculation, grounding public understanding in expert consensus, even when that consensus is less dramatic than alternative framings. The Galileo Project, Lowe's research initiative, focused on systematic search for technological signatures of extraterrestrial civilizations, operates from a stated posture of keeping an open but not empty mind. The motto acknowledges that extraordinary claims require evidence, but argues that dismissing artificial hypotheses a priority before examining evidence is unscientific. This framing positions Lowe and his collaborators as methodological skeptics rather than believers, willing to follow data wherever they lead, rather than constraining interpretations to fit comfortable assumptions. Critics argue that this posture is asymmetric. that Loeb emphasizes artificial hypotheses while downplaying natural alternatives, creating a public impression of evidence for artificiality that the data don't support. The debate is as much about scientific methodology and communication as it is about specific observations. The pattern emerging across ʻOumuamua, IM-1 and 3, I-2, Atlas, is one of escalating ambiguity and richness. Each successive interstellar visitor has provided more data, more opportunities for detailed characterization, and more features that challenge simple categorization. If the pattern continues, future interstellar objects will be detected earlier, observed more comprehensively, and generate even richer datasets that will either resolve ambiguities or deepen them further. Whether that trajectory leads toward consensus that interstellar objects are naturally diverse in ways we hadn't anticipated, or toward accumulating evidence that some fraction of interstellar visitors are artificial remains to be seen. But 3I Atlas, with its combination of robust observations and persistent anomalies, represents the sharpest test case yet for how we navigate the space between natural and artificial interpretations. We need to lay out the scenarios explicitly. Now, what are the competing explanations for 3I Atlas, and what would it take to decide between them? That's the theoretical work of the next section, followed by an examination of why this particular case feels qualitatively different than previous controversies, and what that difference tells us about our readiness to confront possibilities we've historically dismissed. Part 13. Theoretical Scenarios. 3 competing frameworks attempt to contain everything we've observed about 3I Atlas, and each carries implications that ripple far beyond a single astronomical object. Let's examine them with the care they deserve, because choosing between these scenarios is not just an academic exercise. It's a statement about what we believe is possible in the universe and how we interpret ambiguous evidence. Scenario A frames 3E Atlas as a natural megacomet, an exotic but fundamentally ordinary object formed through processes we understand, even if we haven't seen their exact outputs before. The carbon dioxide-rich composition robustly established by JWST's near-infrared spectroscopy fits this framework neatly. JWST found CO2 to H2O ratios around 8:1, far higher than typical solar system comets, but explainable if 3I Atlas formed beyond the carbon dioxide ice line in its parent planetary system. The carbon dioxide ice line sits farther from a star than the water ice line because carbon dioxide requires colder temperatures to freeze. Objects forming in this cold outer region would accrete carbon dioxide-rich ices, while water ice had already been lost to earlier heating or simply wasn't abundant at that orbital distance. Sphere-X mapping of the extended carbon dioxide coma out to distances exceeding 348,000 kilometers confirms vigorous, sustained outgassing, consistent with a large, volatile, rich nucleus responding to solar heating as it approaches perihelion. The sunward tail modeled in the Hubble Space Telescope analysis as anotropic outgassing from a hot dayside hemisphere, fits naturally into this framework. Comets with irregular shapes and non-uniform surface compositions routinely show jets and morphological asymmetries. The extreme aspect ratio of 3 Atlas's sunward feature pushes against typical expectations, but doesn't break them. The recent preprint modeling anti-tail formation through differential sublimation rates of ice-bearing dust grains provides a physical mechanism that reproduces observed morphology without invoking exotic processes. Grains heading sun would sublimate faster, creating an apparent concentration of material in that direction, even though the actual emission pattern might be more symmetric. This is subtle physics, but it's well within the envelope of natural cometary behavior. The polarization measurements, while unusual in placing 3I Atlas outside known comet families in parameter space, are still compatible with natural dust grain populations if you allow for unusual size distributions, shapes, or compositions. Polarization depends sensitively on grain properties, and with only a few dozen well-characterized comets in our reference sample, the parameter space of natural dust is surely larger than we've mapped. 3 Atlas might simply be showing us a dust population we haven't encountered before, expanding our understanding of what coumetry grains can look like, rather than indicating artificial origin. The metal emission, nickel and iron atoms detected in the coma, while puzzling in their ratios and thermal requirements, are now known to occur in other comets. The mechanisms remain debated, but organometallic compounds and radiatively heated metal-bearing grains provide plausible natural pathways. Scenario A's strengths are its conservatism and its reliance on established physics. It requires no new fundamental processes, no abandonment of the assumption that interstellar visitors are natural bodies, no invocation of intelligence or engineering. Its weaknesses are equally clear. It requires stacking multiple unusual features, each at the tail of natural distributions, into a single object. High carbon dioxide, extreme anti-tail morphology, unusual metal ratios, anomalous polarization, near ecliptic trajectory, all individually explainable, but collectively improbable. How many low probability features can you stack before expanding natural diversity becomes a less economical explanation than considering alternatives? That's a judgment call, not a calculation, and different scientists with different prior will draw the line in different places. Scenario B invokes a fragmented interstellar probe, clearly speculative but worth examining on its technical merits. This framework interprets the nickel-rich outgassing as engineered materials ablating under solar heating with nickel-to-iron ratios, reflecting deliberate alloy choices rather than cosmic abundances. Industrial stainless steels and superalloys use nickel concentrations, far exceeding natural ratios, because nickel enhances corrosion resistance, high temperature strength, and other desirable properties. If 3E Atlas were a probe or fragment of one constructed from such materials, and now experiencing thermal stress at perihelion, the ablating surface would release metal atoms with engineered ratios into space. Spectroscopy would detect those atoms as anomalous emissions. Exactly what Lowe claims to see in 3I Atlas's spectra. The sunward anti-tail in this framework becomes a thermal management artifact or a radiation pressure signature. If the object has a reflective exterior optimized to minimize thermal absorption, sunlight bouncing off that surface would create a brightness enhancement along the sun-facing direction that could masquerade as a gas jet in imaging. Alternatively, if the object is actively managing heat through directional ablation, preferentially shedding materials sunward to maximize cooling efficiency, that would create a real emission pattern matching observations. The carbon dioxide-rich coma could serve as an engineered coolant, deliberately used because of its high sublimation enthalpy and inert chemistry. Or it could be a disguise, a coating of volatile ices applied to make the object appear cometary from a distance, while concealing a structured interior. The near-ecliptic trajectory with multiple planetary encounters becomes, in Scenario B, a defining feature rather than a coincidental detail. A probe designed to survey our solar system would naturally choose a trajectory aligned with a planetary disk, maximizing science return by enabling close approaches to multiple worlds in a single pass. The timing, delivering Venus, Earth, Mars, and Jupiter encounters within 6 months, reflects intelligent mission design rather than lucky geometry. The object's size, potentially 5 kilometers or larger, based on brightness and acceleration constraints, makes sense for an interstellar mission, where shielding, fuel, instrumentation, and redundancy all demand mass and volume. Smaller probes might be more fuel efficient, but larger ones are more robust against micrometeoroid damage and radiation exposure over interstellar crossing times, measured in thousands to millions of years. Decisive evidence for scenario B would include structured light curves, inconsistent with random tumbling, repeating patterns that suggest controlled orientation rather than chaotic rotation. High-resolution imaging resolving geometric features, edges, panels, or regular structures would be dispositive. Spectroscopic detection of emission or absorption lines that have no natural explanation, synthetic molecules, or isotopic ratios impossible to produce through stellar nuclear synthesis or natural chemistry would force serious consideration of artificial origin. Radio emissions or modulated optical signals would be smoking guns. None of these have been detected, which doesn't disprove the hypothesis, but means it rests on interpretation of ambiguous data rather than clear positive evidence. Scenario C explores engineered comet disguise, the most speculative framework where 3E Atlas is fundamentally artificial but deliberately designed to mimic natural appearance from a distance. Reflective coatings or smooth surfaces could be wrapped in a mantle of volatile ices, carbon dioxide, and water that sublime under solar heating and create the appearance of cometary activity. The blue smudge from Mars in this interpretation represents a glimpse of the underlying reflective structure, where the ice mantle is thin or absent, revealing neutral or blue-shifted reflectance that differs from the reined dust scattered light dominating at other viewing angles. The carbon dioxide shroud serves dual purposes: thermal management through evaporative cooling and observational camouflage, by creating spectroscopic signatures that observers will interpret as cometry. This scenario is harder to test because it's designed to be ambiguous. A successful disguise, by definition, mimics natural appearance well enough to avoid triggering artificial hypotheses unless you look very carefully at subtle inconsistencies. The plausibility issues are significant. Why would an interstellar probe bother with disguise? If the sending civilization wanted stealth, not entering our solar system at all would be more effective. If they wanted to be detected, overt signaling would be more efficient than subtle anomalies that generate debate rather than consensus. A disguise strategy only makes sense if the goal is selective revelation, being obvious enough to attract attention from advanced observers while remaining ambiguous enough to preserve plausible deniability or avoid causing panic among parking, less sophisticated civilizations. This kind of game-theoretic reasoning about alien intentions is inherently speculative, but it's the logical space where Scenario C lives. Cross-cutting testable predictions allow us to watch for observations that would distinguish scenarios. Refined nickel-to-iron ratios from high signal to noise spectroscopy across multiple heliocentric distances and phase angles would test whether the metal behavior is constant, which would support engineered composition, or variable, which would support natural heterogeneous outgassing. Evolving polarization measurements, as 3I Atlas moves outbound from perihelion, would show whether dust properties change with distance in ways consistent with natural sublimation or remain anomalously constant. IRISE or JWST follow-up imaging could constrain nuclear size and morphology, distinguishing compact reflective objects from diffuse extended.com. Mars-based restacks with transparent methodology and independent verification would resolve whether the blue smudge is real or artifact. Lowe's rhetorical trajectory across his medium essays has moved from presenting 3E Atlas as anomalous to increasingly using language that suggests artificial origin while stopping short of explicit claims. This is a careful dance, maintaining scientific credibility by avoiding definitive statements while priming audiences to consider possibilities they might otherwise dismiss. The strategy works in the sense that 3ie Atlas has achieved far wider public attention than 2I divided by Boris, despite both being interstellar comets. Whether it serves science or sensationalizes ambiguity depends on your perspective. Critics argue it muddies clear thinking by elevating speculation to equal status with established findings. Supporters argue it keeps minds open to possibilities that institutional science might prematurely foreclose. The scenarios lay bare a fundamental question about evidence and interpretation. How much ambiguity do we tolerate before considering exotic explanations? How many anomalies have to stack before natural diversity becomes a less parsimonious framework than artificial design? There's no objective answer, because the question involves prior assumptions about base rates of artificial versus natural objects in interstellar space. If you believe technological civilizations are common and some fraction engage in interstellar exploration, then artificial explanations for anomalous objects deserve serious consideration once natural explanations start requiring multiple coincidences. If you believe technological civilizations are rare, or that interstellar travel is prohibitively difficult, then natural explanations remain preferable, even when they require stacking unlikely features. Because artificial alternatives are even more unlikely by assumption. 3 Atlas doesn't resolve this tension. It sharpens it. And in sharpening it, the candy object forces a conversation about institutional readiness, about whether our scientific and social structures are prepared to handle discoveries that challenge foundational assumptions about our cosmic solitude. Part 14. The smudge that changes everything. Time 0.5 seconds. Return to the image one more time. A faint blue smudge against the Martian night, stacked from multiple mass-cam Z-frames shared on blue sky, amplified through medium, debated across social media, and never officially confirmed or refuted by the agencies that control access to the raw data that would resolve its status. Whether it's a processing artifact, a misunderstood natural coma, or a glimpse of something engineered, the smudge has become the emblem of everything strange about 3i Atlas. It's the visual hook that makes this story accessible to audiences who don't follow spectroscopy or orbital mechanics. It's the ambiguity that fuels endless debate, because neither confirmation nor reputation has arrived to close the question. And it's the leak that broke the narrative monopoly, demonstrating that in the era of public data archives and skilled citizen scientists, institutional control over information is porous and contingent. Parallel truths coexist, and we need to hold both simultaneously. The solid science is real and impressive. JWST's near-infrared spectrograph delivered high-resolution spectra showing carbon dioxide domination, with a CO2 to H2O ratio of 8 ± 1, a robust compositional finding that survives any reasonable uncertainty analysis. Sphere X mapped an extended carbon dioxide coma, stretching hundreds of thousands of kilometers, confirming vigorous, sustained outgassing, consistent with a large, volatile-rich nucleus. Hubble Space Telescope captured morphology showing sunward anti-tail elongation with weak anti-solar tail. Unusual geometry that modeling attributes to anotropic dayside emission. Ground-based spectroscopy detected neutral nickel and iron emission, expanding the sensors of metal-bearing comets and raising questions about emission mechanisms. Polarimetry measurements placed 3i Atlas outside known comet parameter space, though still within ranges that expanded dust grain models can accommodate. These are real datasets from flagship instruments, processed by expert teams, and documented in preprints and papers. They represent significant contributions to our understanding of interstellar object diversity, regardless of how we ultimately interpret their meaning. The leak narrative also resonates as a social and informational phenomenon. The timing, the color mismatch, the silent cycles, the shutdown optics, the multinational data control, all combined to create a perfect storm for speculation. This is not dismissible as pure conspiracy thinking. The gaps are real, even if the explanations are mundane. The ambiguity is genuine, even if natural interpretations are correct. The public appetite for rapid information confronts institutional pipelines designed for careful verification. And in that collision, leaked stacks and citizen science fill voids that official channels leave open. Understanding this dynamic is as important as understanding the object itself, because it shapes how future discoveries will be received and contested. The decision tree for viewers who want to follow this story responsibly is straightforward to articulate, even if it's challenging to execute. Specific future data would decisively tip toward natural versus artificial interpretations, and we should watch for those data rather than letting speculation fill the void. High-resolution nucleus constraints from high-rise JWST or other instruments capable of resolving 3I atlas at small angular scales would distinguish compact sources from extended persistent unusual nickel to iron behavior across multiple heliocentric distances, and observing geometries would strengthen compositional anomaly claims. Polary across wider ranges of phase angles would test whether dust properties are truly anomalous or just unusual within currently mapped parameter space. Reproducible Mars stack detections with transparent methodology and independent verification would resolve whether the blue smudge is real signal or processing artifact. Spectroscopic monitoring, tracking temporal evolution of emission lines, would reveal whether outgassing is stable, periodic, or shows patterns inconsistent with natural rotation and heating. None of these observations are guaranteed to happen. Telescope time is competitive. Mars mission planners have primary objectives unrelated to transient interstellar visitors. Budget constraints limit what follow-up campaigns can be mounted. 3 Atlas is fading as it moves outbound from perihelion, making future observations progressively more difficult. The window for decisive measurements may close before we get answers, leaving 3I Atlas as permanently ambiguous as ʻOumuamua, a tantalizing case study that neither confirms nor refutes exotic hypotheses, but demonstrates how much we still don't understand about interstellar space and what travels through it. The smudge may not be hiding what's there. It may be hiding what we're not ready to see. This is the thought experiment that closes our journey. Assume for a moment that 3 Atlas is artificial, that LOE's anomaly stack is not coincidence but signal, that the nickel ratios and sunward morphology and near-ecliptic trajectory all point toward engineering rather than exotic nature. What would that mean for us collectively, as a civilization confronting evidence that we're not alone in deploying technology into interstellar space? The implications cascade in directions both practical and existential. Practical, because it would validate efforts like the Galileo project and shift resource allocation towards systematic searches for technological signatures. Existential, because it would end cosmic solitude as a working assumption and force us to reconsider our place in what would suddenly become a far more crowded and complicated universe. But now, assume the opposite. Assume 3 Atlas is exactly what mainstream science says it is, an exotic but natural comet from beyond our solar system, formed in conditions we don't see locally, but entirely explicable within known physics. the implications are still profound. We would learn that interstellar space produces object diversity far exceeding what our solar system shows. That carbon dioxide-rich comets with unusual metal emission and anomalous polarization exist and pass through our neighborhood occasionally, and that our theories of comet formation and evolution need expansion to accommodate this broader parameter space. We would also learn something important about ourselves in our epistemology. We would learn that ambiguous data generate passionate debates where prior and interpretation frameworks matter as much as measurements. That institutional science and public curiosity operate on different timescales with different incentives, and that maintaining appropriate skepticism while remaining open to surprising discoveries is harder than it sounds. Both outcomes teach us something valuable. Both push knowledge forward, even though they point in opposite directions. The worst outcome would be permanent ambiguity, where 3E Atlas fades from view before decisive observations resolve the core questions, leaving us with a rich data set that supports multiple incompatible interpretations and no clear path to choosing between them. That's where ʻOumuamua sits today, still debated years after it left the inner solar system, still invoked by both natural and artificial hypothesis. Advocates are supporting their positions. 3 Atlas risks the same fate unless follow-up observations arrive soon enough to matter. The call to action is simple. Watch for the exact releases that matter. Monitor whether high-risk constraints appear in Mars Reconnaissance Orbiter archives. Check for JWST or ES emission follow-up observations appearing in preprints or press releases. Look for independent analyses of the Mastcam-Z frames if NASA makes them publicly available with sufficient metadata for reproducibility. Follow whether nickel-to-ion ratios persist or change as more spectroscopy is published. Track whether polarization measurements are refined with additional observation. These are the data points that will move the needle, that will either close the ambiguity or deepen it further. And while watching for data, maintain appropriate epistemic humility. We don't know what 3I Atlas is with certainty. We have measurements, models, and interpretations, but the measurements are finite in number and precision. The models contain assumptions, and the interpretations reflect prior that differ across observers. The blue smudge from Mars, real, or has already changed the conversation by making the unthinkable thinkable. It's made millions of people aware that interstellar objects pass through our solar system, that we can observe them with increasingly sophisticated instruments, and that what we find might surprise us in ways that challenge comfortable assumptions. That shift in public consciousness has value, even if 3 Atlas ultimately proves to be a natural comet. It prepares us for a future where interstellar visitor detection becomes routine, where ambiguous cases like this will recur with higher frequency, and where we'll need frameworks for thinking about evidence and inference that most of us haven't developed yet. Maybe the smudge is showing us exactly what's there. A faint detection of carbon dioxide coma seen from Mars's unique vantage during a close encounter, colorized blue through processing choices that don't reflect physical reality. Maybe it's showing us nothing, an artifact of stacking methodology or instrumental quirk that happens to fall at coordinates where we expected to find something. Or maybe, just maybe, it's showing us what Lowe has been suggesting all along. A glimpse of reflected light from a surface that wasn't formed by accretion in a protoplanetary disk, but was shaped by intention in a fabrication facility, orbiting some distant star, launched toward our solar system thousands or millions of years ago, and only now, revealing hints of its true nature to observers skilled or lucky enough to notice the discrepancies. We don't know which. We can't know which. Not yet. Maybe not ever. If the follow-up observations don't materialize or don't resolve ambiguity, what we can know is this. 3E Atlas represents a test case for how we handle discoveries that exist in the liminal space, between natural and artificial, between comfortable and unsettling, between what we expected to find and what we might actually be seeing. How we navigate that space, as scientists, journalists, and engaged citizens, will shape not just our understanding of this particular object, but our readiness for whatever comes next. Because whether 3 Atlas is the third natural interstellar comet or the first confirmed artificial interstellar probe, it won't be the last strange thing we detect passing through our cosmic neighborhood. The sky is vast, the galaxy is old, and we've only just started looking carefully at what moves between the stars. The next ʻOumuamua, or 3E Atlas, could be detected tomorrow, next year, or a decade from now. When it arrives, we'll be better prepared if we've learned from this case how to balance skepticism with openness, caution with curiosity, and institutional expertise with distributed verification. The smudge, whatever it is, has given us that opportunity. Whether we take it is up to